Welcome everybody to the Geospatial tutorial. I'm Serge from the University of California, Riverside, and it's my privilege to be one of the co-chairs for the SciPy meeting, so welcome. How many of you, this is your first SciPy? Excellent, so that means it's your first workshop here as well? Good. This is going to be a joint effort between myself. You want to introduce yourself, Joris?
Yeah, so I'm Joris. I'm from Belgium, working in France currently, and one of the geopandas maintainers. So,
and then we also have Levi Wolf, University of Bristol, works on the PySAL team, and Danny Arribas-Bell, who's at the University of Liverpool, also on PySAL. So this is a joint effort between geopandas and PySAL. First time we're doing this, so it should be exciting. So it's going to be a four-part session. Yours will start, then Danny will take over, then we'll have the break probably, and then the second half will be myself and Levi. So because there's four of us, we have chances to help if people are stuck with the installation or have questions while we're going through this. Are we going to talk about the binder?
Yeah, so if you don't get everything working and installed, but you want to follow now because we are going to start, you can try, there is a button on the GitHub repo, launch binder, and normally, so that should create a working environment with all the materials online. It may not be the fastest, but it's should be a backup if in case it is not working locally. So that's something that you can try. Maybe to start to get a little bit an idea, who has already used geopandas before? Some of you? Who has already used PySAL or related libraries? A few, a bit less. For those that didn't use geopandas yet, did you already use pandas library itself? Yes, most of you did? Yeah. So that's good, because we will assume a little bit that you're familiar with pandas. We won't explain everything of pandas, so that's will be helpful that you are familiar with that. So we are going to start with, so the first part will be an introduction to geopandas and related libraries, to start working with geospatial data, reading in data, doing some queries on it, do some manipulations, and then after the break, we'll go to the PySAL part, which is more than the spatial data analysis, data science part. So to get started, oops. So in case that's a question. Who is not familiar with Jupyter Notebook? Everybody is familiar. You maybe used it for the previous tutorial as well. So that's good. So we start the notebook in the directory that you downloaded or cloned with Git. Then you should see something like this. Increases a bit. And so we are going to start with the first notebook, notebook 1. Introduction to geospatial data. Is this big enough to be readable in the back? I can increase it a bit more.
Is there a way to turn off those lights?
Yeah, probably yes. Good question.
Yeah.
That's better. Okay. Okay, so maybe another question. Who of you followed the CartoPy tutorial yesterday? A few. So you can explain what the difference is between raster and vector data? Somebody wants to try? Or give an example? What are the examples that were given in the tutorial? Yeah, indeed. So the vector data, it's here in the title as well, geospatial vector data. The tutorial will mostly focus on that kind of spatial data where we have polygons like neighborhoods in a city, points, line strings. So that's the type of geospatial data that we will mostly see in this tutorial. On the other hand, we also have raster data. Think typically satellite images, where you have images with pixels. So we will mostly focus on vector data. And because vector data, if you have points, you have a set of points with, let's say, points of interest within a city, you often have additional information about those points or polygons. You have attributes about those points, and that fits. You typically want to put this in a table where you have different attributes for each point. So each row are the metadata linked to a certain location in space. So therefore, that fits very natural in a table, and then in Python using a pandas data frame. So that's the kind of data that we will start with. And the first thing, if you want to start with that, of course, is we have to get some data. And yeah, in GIS, in spatial data, you have many different file formats, also some very specific file formats, like shapefiles, GeoJSON files, geopackage files, and GeoPandas provides provides an easy way to read in all those different data formats using the GDAL library under the hood. So the GDAL library is used it's a very base library for the full open source geo ecosystem, used in many libraries applications for reading and writing data. So here's a small example. In the material that you downloaded, we provided a zip file that we got from Natural Earth Data with all the countries of the world. So we can use the GeoPandas read file function to read in those data. And if you look at the first few rows, you see it's a data set, all the countries of the world. You have the name of the countries, the continent on which is located, the population, GDP, and then here there is a column called geometry. So that's important to see, to know, because we read it with GeoPandas. We go back to the geo-data frame. I will explain a bit the difference with the normal data frame. There is here a geometry column, and in this case it are polygons because our countries are polygons. We can also quickly plot it. Now, so you will see we have all the countries of the world. Yeah, so those things I explained. So,
Can I ask a question?
yeah, for sure.
This is very simple plotting the countries, but if you would have another data set, I mean, does this plot function know which the data set is in, so it can plot it correctly, or is it so rough you don't want to plot anything?
The plot method itself is naive to that. It will just plot the coordinates that it gets on the map. But there are, we will see later on, methods to convert and make sure that it's okay. But that's something in GeoPandas that you have to do yourself to make sure that both are in the same coordinate system and things like that.
Yeah.
So what we got the countries data set. It's a geo-data frame. And as I already explained, so we have our geometry column, and then the other columns are the attributes of those geometries. Some special things about this compared to a normal data frame is that you can always access this geometry column with a .geometry attribute. And this gives us a geo series. So it's like a geodata frame is a subclass of a data frame. Geo series is a subclass of a series. So it has all functionality of a normal series, but it has some additional functionality, some additional methods and attributes specific for the type of data, for the geospatial data. So as a small example, we can get the area of each polygon with the area attribute on our geoseries. And we will see later on in the tutorial many other methods that are available on the geodata frame and the geoseries. It's of course still a data frame, so we can, so everything that you know from using pandas will still work. Like we can access the population column and calculate the mean like this. Or what we can do is we can filter our data set. We can take a subset of our data set. In this case, so I get the continent column. I compare it with Africa. So this will give you true false. It will give you a Boolean series. And because it's a Boolean series, we can use it to filter our original data frame like this. So to only get all the countries that are that have in the continent column Africa, and in that way you can easily use a familiar pandas syntax to take a subset of your data. In this case, all the countries of Africa. Yeah. So here a summary of what I said. So the geodata frame will allow those specific spatial operations. So up to now we have seen a small example with polygons, but as we already said in the beginning, you can also have points, you can have lines or line strings in the terminology we will use here, or you can have combinations of multiple points, multiple lines, multiple polygons in a single geometry. So in this case for our countries, it's a bit a long representation, but so this was a polygon. So now we are going to import a few other data sets, also from Natural Earth websites. So I have one with some cities. The cities are represented by points, and some rivers, which are represented by a line string. So it's a line. If I would get here, change this print with a type, you will see that this is a shapely line string. So shapely is a library that GeoPandas uses under the hood to represent those points, lines, and polygons, those geometry objects, and it's also the library that provides all the specific geospatial methods. It actually does it by itself interfacing to the GeoC library, which is, for example, also used by PostGIS. So it's actually the same C library under the hood as PostGIS that provides all the functionality for GeoPandas. Up to now, we read data in from a file. If needed, you can also construct some points or polygons yourself. For example, here with the point, you provide X and Y, or longitude, latitude. Or with the polygon, you provide a list of coordinates. So very easy. Further on in the tutorial, we will also see quite a lot of methods that are available on a geodata frame. Important thing to remember is that often those will also work on individual objects. For example, for the polygons, I saw here a bit above the area that you can, with the area attribute, get the area of each. So where was it? Here, with the area attribute, get the area of each polygon in my series. If I have a single polygon and I want to know, so this single polygon, I can also get the area of that. So it's a very, mostly a one-to-one mapping of methods for the geoseries or the individual objects. So then, related to the question we had before, and certainly, so the people who follow the SciPy tutorial will now be quite familiar with the importance of projection system for having something on a map. GeoPandas is, for the rest, as I said, naive to your coordinate reference system. It will not do automatic reprojection or something like that. So you need to ensure yourself that, for example, if you are plotting multiple things together, that they both have the same coordinate reference system. But it provides some functionality to do that. So a geo-data frame has or a geoseries as well, has a CRS, so for coordinate reference system attributes. And in this case, you will see here, for the countries, that we have EPSG 4326, which indicates that it's the most widely used, just longitude, latitude, based on VGS 84. We can then plot this just without any specific map projection, but we can also change. I will here. For example, we can use the 2CRS method to convert our geometries from one coordinate reference system to another. An easy way is to provide the EPSG code. So every or most coordinate reference systems have such a code. Here I put a link of one. On that website you can also search for the correct code that you need. But in this case I'm going to convert our coordinates to web Mercator, or world Mercator in this case. So with 2CRS, you will see that if you look at the data, so before, now you see here numbers within the 0 to 180 range, because this was in latitude, longitude, latitude. If you now look at the new one, you will see now this range is much higher. And if we also plot it, you will see that it has now a different projection. And Greenland is much bigger than it was before. Now, in the SciPy tutorial we saw why are those projection systems or map projections and in general those coordinate reference systems important. For example, if you want to plot things, you get all different options. Also, those conversion functionality is also important if you get different data from different sources, and often they are provided in different reference systems, so you want to convert them to a common one. Or specifically for GeoPandas, the second point here is also important. So you can calculate distances with GeoPandas, but it will just assume that your coordinates are in the Cartesian plane, and for that, if you want to have a distance metric that you want to understand, like how many kilometers are my 2 points from each other, you typically want it in meters and not in degrees. So if you have a data set in longitude, latitude, and you want to calculate distances in meters with GeoPandas, you need to convert it to a coordinate reference system that has a meter unit and not in degrees. So that's another good reason in GeoPandas that you might want to do this. Okay, so to end this initial introduction, and then we'll get to some exercises. Here's an example how you can plot different things together, because I already showed how to plot the countries data set. We will assign the result to an ax, which is a matplotlib axis object, so we can use that to add the other plots as well. By here providing that I want to plot my rivers and plot my cities on the same map. And for the rest, it's also based on matplotlib, so the typical ways to style the plots are available here as well. In this case, I say I don't want any fill, no face color. I don't want to fill my polygons. I only want to have an edge around it, and the cities have to be in red. So that looks then something like this. So there are the points, the line strings, and the polygons. Okay, are there any questions up to now about this part? If not, we will go to the notebook with a bigger exercise so that you can start practicing a bit. It's this one. So case conflict mapping that you can open. I will give you a short introduction about the dataset, and then you can start with the exercises. So the dataset that I provided here is a dataset about artisanal mining sites in Eastern Congo. So it's an organization, the IPS, from which I got the data, did like visits of mining sites and inspected the different mining sites so that they have data on how many workers are there active, if it's controlled by an armed group or not, what minerals are they mining. So it's a survey on mining sites in Congo. So you have some background there. They provide a public API to get the data. So I put here an example how you can do this with directly interfacing with their API. But let's start with the exercise to read the GeoJSON data, because you can also download it as GeoJSON. So this data set is available in the data directory in the repo. So the first exercise is to read the data from the GeoJSON file and inspect the first inspected bit. A final note before you can start. So I would advise you to really try it yourself, but if you are stuck and we are not available, I would first try to ask us to give you an explanation or give you a hint. But if you want to see the solution or you're ready and you want to compare it, you can always comment this out and run the cell and you will see a possible solution. Okay? It will not be exactly the same as your solution maybe. That doesn't mean that your solution is bad, because there are often several ways to do something. But in that way you can check it, and you can maybe already go a bit further if you are somewhat faster than as we are going. Or so you can try with that exercise. If you're ready, you can run the code here and do the exercises below as well. So you can certainly already go until here point 2. I will go through some of the first exercises and highlight some questions that we had. So to start with, to read in a file, we use geopandas read file, and then we pass the directory or the file name, the path, like this, and we call it data visits. Oops. so we know the pandas functionality to check the first few rows. And just to give you a bit, so an idea, I will show that later. So because there are quite some columns and we don't need all the columns for the tutorial, so I provided here some code to select a subset of the columns. And if you now look at it, so what is the data that we have here? So we have point data, and so our mining sites are points. We have an indication which mineral is mined there, whether there is an armed group, the number of workers, and then a name of the mine, some ID, etc. And a date when it was visited. I provided here a little bit of code to create a subset of the data. So we are only going to take those that were visited by IPs. So by again doing a Boolean filtering operation here, where for all rows where this column contains the IP string, and also where there are at least more than 0 workers, so the active mines. And I still sort them by date. Some mines were visited several times, so I deduplicated by grouping by the code and taking the last one. So the last, if a mine was visited several times, we take the last one. And finally, convert it back to a geodata frame, because by doing the group by, we lost the fact that it was a geodata frame. So now what we have here, the data here has still, so we have now a data set with a bit more than 2,000 mining sites. The other data set that we are going to use throughout this exercise is a data set on protected areas, so natural national parks in Congo. So yeah, we again provided the link where we got the data. I will just show here the results. So you can, if you do it similarly, sorry. Oops, I have here apparently not the latest version. So if we did it similarly as how it was, sorry, this zip file. Yeah, thank you. So this should work, I think. No. So apparently, so yeah, the same thing. Apparently some people already had that problem.
It's not working because the zip file was just renamed cause something or other, but it was zipped as conservation/RDC, blah, blah, blah. So inside the zip file, it still has different names.
Okay. Sorry for that. So let's go to quickly check the so if you look in the data directory, yeah, so normally zip files also work like I already understand. Okay, so the problem is indeed shapefiles are annoying. That's actually the reason. Because shapefiles, for those that are not familiar with shapefiles, it's a file format, but it's not a file. It are actually multiple files that you always need to have together. That's the reason that people often make it a zip file or an archive, another archive. But then, yeah, depending on how you zip it, and the support for reading it directly from a zip archive is not, I mean, it works because we used it in the previous notebook, but it doesn't work always depending on if it's still in a sub folder in the zip file or things like that. So in case it doesn't, you don't get it working with the zip with the archive, you can simply unpack it and then point to the directory or one of the shapefile inside it. Doesn't matter, both work.
That works.
Yeah, and that will work. So I suppose that this will not work because I didn't unzip it. If you want it from the zip file directly, I put here, because it's a bit complex in this case, I actually put it here. You can do it with this line, but since that's quite complex, the easier thing in this case is to unpack the zip, the archive, and then you can read it like this. So you can either copy paste this one and comment that one, that will work with the zip file we provided, or unpack it and do it like this. I will just, so. So to quickly have an idea of what is inside this data set, so we do a plot. So you recognize a little bit the outline of Congo in here. So here are polygons, and each polygon is one national park. So for example, if we look at the protected areas ahead, you will see that there are quite some columns, but the last one, our geometry column, are polygons, and somewhere in it there is a name of the name of the national park. Okay, we'll give you again a bit of time to get here, and you can further continue with this part of the exercise. So if you didn't succeed with reading in the files, the working line was inside the solution. You still have an hour for the, we'll now go through it, and you have a small hour for the. Okay, yeah, we have quite some material, so it's not no problem if you're not ready yet, but I will go quickly through some of the solutions, and then we will switch to doing some actual spatial operations. So you might already have noticed, so the data, if we check the coordinate reference system of both, so you can see, so both have a different coordinate reference system. So, for example, yeah, it's actually in the second, so I will first show this. So, if we would like to make, because we now have the areas and the points of the same area, so to see their relationship, we want to plot them together. How can we do this? We can plot our data. This returns an natural deep axis, and then on I also want to plot the protected areas on this axis, and let's say that I want to use a green color because they're national parks. So you already see, if you plot it, because GeoPandas is naive to the current reference system, you see it doesn't match, so we need to first convert our two data sets to a common reference system. Another reason that we would like to do this is if we want to do distance-based calculations. For example, here we are going to import from Shapely a point to create a single point like this. So in this case, I need to use those coordinates, but be careful. So in GeoPandas and the same in SciPy, it's always longitude, latitude, so x and y. So be careful about the order in which you put this here. So the 1.66 is south. So north-south is our y, and we need to put this last, I think, if I'm not mistaken. So like this. And then we can, the question was, calculate the distances of all mines to this point, and then find the five smallest ones. So the 5 mines closest to Goma. Goma is one of the bigger cities in the Kivu province, near the border with Rwanda. So how do we calculate this? We have our mining sites. We can use the distance method for this. And if we give it a single point, it will calculate the distance for each of our points in the data set to Goma. So, and if we now want the 5 closest one, so we want the smallest distances, we can, for example, sort those. So they will be ascending. So the 5 first values are here. But of course, 0.38, it doesn't say that much in degrees. So if you want to use GeoPandas with distances, you again need to convert your current reference system to something in units that has a meter as unit and not in longitude, latitudes. So now, so both are reasons to convert our current reference systems. So let's convert them. So the first one was, as already showed before, so the longitude, latitude here. Apparently, so it was provided by the data as we downloaded it. It was in World Mercator, and we will convert both to the local UTM zone. So typically, if you have data that are not spanning the full world, but a certain country or certain city, you can use the local UTM zone and your spatial, so you won't have big distortions in the shapes or in the distances that you calculate, as long as your data are relatively fitting proper for that UTM zone. So again, you can look here at a link that will indicate for which area this UTM zone is appropriate. How do we convert our data? So remember, we can use a 2CRS method, and then it's provided here. We want to, we want to use this EPSG code, so we can provide that here, like that, and that will convert. So our data was in longitude, latitude, and now you see this is no longer the case. So we can call this UTM. I will then quickly show the other one as well. Oops. So we can do this for both. So for both the data, the mining sites are the protected areas. And if we now plot them together, you will see now they are in the same area. I will give this a green color, like that. and make the points maybe a bit smaller. So we can use here at the typical matplotlib keywords to style our, is that smaller? Yes, like that. We can, for example, give it some alpha to have it overlay. Yeah, there are too many points to really see the effect of this, but so you can use the typical matplotlib functionality. In this case, we want to maybe also set our axis off if we don't want. So what this function will do is just remove the full box around it with the because in this case those X and Y labels are not that interesting, so we can set this off, and we can also make it, for example, a little bit bigger. Let's say 15 on 15. So like this. So the next exercises, I try to do this a bit in a few steps to quickly customize the plot a little bit. So you can always go through if you want those exercises, but for the tutorial now we will switch to some actual spatial operations, and for that you can open the second notebook, so notebook 2, spatial operations, relationships and operations.
How's that? Can people read these? How about at the very, very back? Can people read these, more or less? Yeah, no binoculars required. Cool. All right, well, so welcome everyone to the second part of the workshop of the tutorial. I'm Daniel Ribesbel from the University of Liverpool. And in this second session, what we're going to do is looking at what's called spatial relationships or spatial predicates. So how can we put in relation different observations that have a location pinpoint, right? So before anything else, let's go ahead and import pandas and geopandas, and let's read all of the data to make our life easier later. And this is almost like going back to to middle school when you had different shapes and different objects, and you wanted to combine them in different ways. So there's a bunch of different operations we can do, and the GeoPandas supports. And the ones we're going to look at today are of this kind. So if we have two objects, and these two objects could be a polygon or a point or a line, so all vector objects, we can check whether one is within another one. We can check whether two touch each other. We can, and that that could be for the case of polygons, which we'll build up later on in terms of the contiguity concepts that Serge and Levi will look at later. Or whether a line is touching another polygon, whether two lines crosses, so crossing of objects, and again that could happen between two lines. If you're looking at roads or streets, that could be very useful. Or if you have a polygon and a line, as we'll play in a little bit, or whether there's an overlap, and so on. So this is a few examples. There's a whole list of spatial relations, and like for everything that matters in life, there's a page on Wikipedia for that. So I won't bother you a lot more with that for now. So let's start. The way we've designed this is, first we're going to look at these relationships at an individual level, so at an atomic level. So say you have a polygon or you have a point or a line, and you want to check whether that point is within a polygon or whether the line is crossing the polygon. And then that's useful, and conceptually, I think for me at least, is the most useful way to get my head around what GeoPandas at the end of the day is doing. But then in most cases, you won't have one polygon or you won't have one line. You'll have a whole street network, which is made up of segments, and you want to check for each of them, and you don't want to do that manually. So GeoPandas makes it very easy to broadcast those operations across a lot of observations. So before anything else, let's get started with atomic relationships. So you can tell that it wasn't me, it was some Belgian on the team that wrote these exercises. And let's just pick a random example here and pick the country of Belgium. And then we can actually, well, actually, I'll first go over what this does. So what are we doing? We're querying the country's data frame, and we're keeping all of the observations where the name column equals Belgium, which there's only one last time I checked in the world. And then for the entire row, we keep only the geometry column, right? And then that will still give us a geodata frame. And because what we want to query exactly is the geometry, we use this helper here called squeeze, which if there's only one observation in a geodata frame, will squeeze it into a geoseries. And because that's only a single column, it'll really squeeze it into the geographic object. So if we do that, the notebook has a really nice rendering printing method. So when you just run Belgium, you'll get the shape of Belgium. So object number 1. Let's do the second one, Paris. There's another member of the team that happens to work in Paris, even though he's not French. So let's pick Paris and Brussels as 2 points, and they'll give us 2 point objects, right? And the approach we take to do that is exactly the same. We query the data frame, we keep the geometry only, and then we squeeze it into the geographic object. Yeah?
Quick question. So when you just created that map of Belgium there, you didn't call matplotlib. So there's a built-in method
Yeah.
within GeoPandas that you sort of
Yeah. So the question is, very good point. I just said Belgium, and all of a sudden it plots Belgium. I didn't have to say Belgium plot, right? And the reason is because, so actually let me very quickly show you the difference, yeah. So if I do this, it's going to print the polygon, and then it's going to plot the polygon. But because Belgium is already the polygon object, there's a built-in rendering quick print on the notebook that will print the polygon. And this is only just for a quick check-ins, because you can't really use it to combine different shapes or anything. It's not, it's just a quick lookup, so to speak.
But this is built into GeoPandas, not Jupyter.
Well, that's a good question.
It's a shapefile object, as you can see. So it's just like a rich representation of the shapefile object.
Yeah.
If you actually want to see the coordinates, you need to do a print statement.
Yeah, no, I'm just saying that this must be part of the package that we imported because
Yeah, but it only works on Jupyter,
there only works in Jupyter.
on notebooks, or in the rich console display.
It's a shapely, special, pretty reprint for you.
Yeah, so it's equivalent to, I don't know if you've noticed, pandas data frames. If you print them on an interpreter, they'll print as a string. If you print them on the notebook, they'll render as a nice HTML table. This is equivalent to that. Yeah.
It's the underlying geometric library, not GeoPandas itself.
Yeah.
Okay, thank you.
Yeah. So then we do the same for 2 points, Paris and Brussels, and we can see if that gives us also a similar representation, but because it's a point, it's not terribly useful unless you have multiple points or more complicated point objects, right? But it's there, and sometimes I actually use it a lot when you have to, when you don't know your data set and you want to make sure that it's what you think it is, and if you think it's a point, it'll print a point. At least you're in business. And then finally, let's create. So we have 2 points. We have a polygon. Let's create a line. For that, what we do is we import the class line string from Shapely. So this is another geographic or geometric object. And it's really, the API is really neatly designed. So all you have to pass is, well, you can create it in different ways, but the simplest one is you just pass a list of separate points, and they'll give you a line that goes from point 1 to point 2. And so in this case, we're just creating a line that goes from Paris to Brussels. And same as with the other ones, again, this line is not terribly complex, so this doesn't help us a lot. But if you had a more intricate trajectory, it would still render it, and it can be useful to explore. And then we can also combine. So we have, once we have object, like everything else in Python and pandas for data, we can combine them very, very easily, right? So in GeoPandas, we can create a geoseries that actually has different geometries. So usually you wouldn't, well, I'm not going to say, in most of my use cases at least, you wouldn't want to have in one data set different types of geometry, so you wouldn't want to combine points with polygons with lines, but you can if you want. And it's really easy. Again, you can create a geoseries that Joris presented before with a list that just includes all of the objects, and then we can pipe it directly into the plotting function, and that'll give us a plot. And then this is, to go back to your question, this is not the light representation. This is a full-fledged matplotlib plot, right? That it's combining all of the objects in the geoseries. Okay, so I'm going to switch gears a little bit. And the way I'm organizing it is I'm going to give you 2 minutes for a super quick example. So all of you kind of come back from sleep mode while you were pretending to listen to me. And I'm going to ask you to create a similar figure to this one, but that connects France, Spain, Paris, and Madrid. And then I'll give you a prize if you can guess where I'm from. And it's not France. So I'm going to give you 2 minutes very quickly to try to recreate a similar plot to this one, but with France, Spain, Paris, and Madrid. And if you have any questions, just please raise your hand and we'll be moving around. Okay, I'll move in just to keep it more dynamic, but I'll post the exercises to the GitHub repo later, but they're here. Just 1 sec. So you should have got something similar to this. How have I done it? First, I pull out Spain the same way. We just query the data frame for everything within Spain, keep the geometry and squeeze it into a geometric object. Same for Madrid on the cities data frame. Then France and Paris, we already had it. And then we throw everything into a list that contains Spain, France, Madrid, Paris, and then on the fly we can build a line that goes from Paris to Madrid. All of that gets squashed into a geoseries, and then directly we pipe that into the plotting engine. Yeah? Any questions?
What DOM did we get from France?
What? Sorry?
What department did we get from France? That little speck of.
Oh, that's because it's a complete map. So, oh no, I called it France, FR. So France has the colony, well, the old colonies.
So I was asking which colony is it?
What is it? Guyane, France has? The French Guyane? I wouldn't say. You're testing my geography.
Probably La Réunion is too small to speak on.
Yeah. I don't want to go on the record, but I would say it's the French Guyane. Not that I work on a department of geography or anything, but all right. So that's a quick way for pulling out geographies and then playing with them very easily, right? But then what I said we were going to do in this notebook is, well, now that we have a couple of points, a polygon, a line, we want to learn how to put those in relationship, right? So how can we check whether the point of Brussels is within Belgium or the point of Paris is within or not Belgium, and so on. And of course, in this toy example, this is all very obvious, but the logic is the same when you want to blow it up to a much larger data set, right? So let's start with the simple stuff. So we can query whether Brussels is within Belgium, and this almost reads like English, and then we get a return true, right? So under the hood, what it's doing is taking a point object and doing what's called a point in polygon operation with the polygon that we pass for Belgium, right? And we could do the same for Paris. Is it within Belgium? Is not, right? And it'll tell us false. This is using the point as the reference and then calling the within operator, we can also say flip it around and say, well, if I have a polygon, the polygon can contain a point or not, right? And then we can say in this context, does Belgium contain Brussels? True, right? We could do France contains Brussels, false. Yeah? So that's for contains and within, it's the two sides of the point and polygon coin, right? And in some cases, if you have a lot of polygons, you might want to use contains, or with, and if you have a lot of points, you might want to use within. It depends on what your ultimate goal is. You want to use one or the other, and it'll be more useful. Oops. So that was points and polygons. Now, what if we have a line? So let's go back to the line where that was going from Brussels to Paris, which is yours is commute. Does Belgium contain it? Well, no, right? Because it goes, part of the line goes within Belgium, the other part within France. So again, the contains, what checks is whether the object on the left, in this case the polygon, fully encapsulates the object on the right. And again, you can flip it around, and well, not flip it around. You can use the intersect to see just does it cross. Is there any sort of a touching between this polygon and this line, even if it's not complete? So the line might not be fully within the polygon, but is it part of the line inside the polygon? You can use the intersect, and the line does intersect. Yeah.
It's interesting that in my notebook it's rows and arrow at this point as an unsupported operation. But it runs with you.
It's. Does it? So your problem is that.
That line shows an arrow line 22 in my notebook.
This line is a line like that.
Yes.
Okay. So.
Anyway,
Yeah. Well. Okay. Any questions so far on these basic relationships? All right, so then I'll move on. And then I said, well, this is very useful conceptually, right? If you want to understand under the hood, well, how do you do it at an atomic level? Say if you have a point and you have a polygon, or you want to put in relation a line and a polygon. But usually in real world, we don't have one line and 2 points. We'll have a load of points and a load of polygons. And we want to use those. We want to use these sort of relationships comfortably with larger data sets, right? So happily for us, GeoPandas does that very easily. It basically broadcasts everything that or almost everything you can do at an atomic level. It'll do it efficiently at a data frame, geodata frame level. Yeah. So remember how we said, whoops, Belgium contains Paris false. That was one polygon, checking whether one polygon contains a point, but we actually happen to have a lot of polygons in our countries data set. So we can say directly countries contains Paris, and what it returns is a column of booleans. So for every row in the country's data set, so for every country in this case, it goes and checks whether that country contains the polygon of the point of Paris, and then it returns the output. So this will only occur once, right? This will be true only once.
And depending on whether or not you identify how large a threshold you have for your city, since there is a Paris, Texas. Just
Fair enough. Yes. Okay. Yes. Yes, that's true. I don't think Paris, Texas is in this data set. But then, again, this is the heavy lifting. In line 25, the heavy lifting happens. All of the checking, the computation required to check happens. But then actually for humans like me who don't like to read false and true, but actual names, you can then use this in combination with the standard pandas logic for querying data sets or data frames to subset the country's data frame to only those lines where the countries contains Paris query is true. And we can just do this, and in this case, yeah. Maybe we should expand it to have a Texas country that has Paris in there and makes it true. but that, again, there's nothing spatial that happens in this line, but this is also really useful to show that a lot of the pandas logic for manipulating tabular data sets applies entirely here. It's just that we're expanding that with geographic capability or geospatial geometric capability, really. Yeah?
Question.
Yep.
Is that a new object or just a view of that slice of the data frame?
This is a query, so I would imagine it's a view. I mean, it's whatever pandas would do in the standard. So it's exactly.
That's a Boolean, not a slice, right?
No. It's the same way of querying a data frame here, right? So I'm not sure exactly whether that that would be, what would that be? A copy or a view?
I think it's a view.
It's a view, I would say. Yeah.
No, it's a copy.
It's a copy.
Let's discuss that offline.
Because it's
We can discuss that a very long time. We'll do that in the break.
So it's a copy, yeah, okay. All right, so, but in any case, that would, there's nothing specific to GeoPandas when you do that query. That was my point, right? And then here's another quick example. That will work with any sort of geometry that GeoPandas supports, right? So in this case, we can pull out the Amazon River. In the same way, we query the Amazonas River in the rivers data frame, keep the geometry, squeeze it in, and then we can look at which countries cross the Amazon or intersect. And it'll give us, well, Brazil, Colombia, and Peru. Yeah? And again, we're using, at the core, it's a geoquery, the crosses one, that returns a Boolean, and then we pipe that into a simple filtering for a data frame, for a pandas data frame. And that will return the countries we want. And so far we've seen the crosses, the contains, the intersects. There's a full reference here, and again, these all built on the so-called DE9IM model for predicates and geographic objects. There is a Wikipedia page for that if you want to read, and if not, the Shapely tutorial, the Shapely manual on this is fairly comprehensive. So if you're really interested in the details, please go there. So with that, another 2-3 minute quick exercise for you to shake off my boring voice. Can you find all of the countries that are contiguous to Brazil in the data set? And here's a hint: by contiguous, I mean countries that touch Brazil. Yeah? So I'll give you 2 minutes, something like that. It's French Guyana, right? And French Guyana does touch Brazil. So France is a neighbor of Brazil, see? Here's one lesson you can walk out of this workshop that you probably didn't know. On the Python side, there's a couple of things you could learn from these. First thing, we just pick out Brazil. Same way, we query for the name Brazil, we keep the geometry, we squeeze it into a geometric object, and then all of the heavy lifting happens here, countries that touches Brazil, and then we just filter on the countries data set to keep the rows. Yeah? Any questions here on this method, on these ways? No? Cool. So then the final part of this notebook is covering spatial operations. So far we've talked about spatial relations, right? So how can we put in relationship two objects and check whether they meet the requirements of different types of relations, whether they touch, whether they cross, whether they intersect, and so on. Now, another big set of GIS functionality, really, or geometric functionality in GeoPandas is about spatial operations. So things that you can do, you can create based on geographic objects, not really just checking for existing objects, but creating new objects that follow some sort of rule that you're interested in. And again, I'm not going to cover all of them because, I mean, we could spend a whole day on Shapely, really. But if you do learn the basic grammar, it all pretty much works the same, and the patterns are the same. So the kind of objects you get back would always be geoseries or geo-data frames, and really it's just getting into what the spatial operation you're interested in will do. Okay, so a very common operation is buffers. So if we have points, or if we have any object, but the easiest one to understand is if we have a point, we can draw a buffer of a radius of x meters around it, and then that really is a polygon, a circular polygon. And that's very useful to combine later on with all of the relation operations that we've just seen, right? So if you want to see whether any point is within 500 meters of another point, one way to do it is checking distance. Another way to do it is create a buffer for that point and then check for pointing polygon with the other ones. So the real power of all of these comes not at the atomic level, but when you start combining them, all of the different ones, and putting them together. And because at the end of the day, everything happens in the same Python objects. It's all shapely geometries stuffed into geodata frames or geoseries. It's all very, very easy to combine and put together, chain one after the other, and then build fairly complicated operations at the end of the day. So in this case, what do we have is just a simple plot of the polygon of Belgium that we had before, the Brussels location, and then around Brussels, we've drawn a buffer of 0.5. Can anyone tell me what 0.5 means here? Because usually you want to say, well, I want a buffer of 500 meters around my point of interest, or what is 0.5? Does anybody remember from? It's degrees, right? Because our data right now, they're expressed in longitude and latitude. So if you wanted to do distances, as Joris said before, you need to convert the CRS to something that's expressed in meters or miles, and then run create a buffer around it. And then in that case, you could say if you had converted it into something that's expressed in meters, you could just pass 500, and that would be a 500-meter buffer.
If you create those points and then convert, will the shapes morph from a circle to the...
Yes. Sorry, what? Say the question again, because...
So if you create a buffer in degrees and then you convert it to a different CRS, will the corresponding buffer projection?
Yes. So the question is, if you say you have a point, then you create a buffer around your point in long lat, and then you convert that buffer into a different CRS, right? So the answer is, if you convert the buffer, yes, because at the end of the day, the buffer is nothing but another polygon object, which if you can convert and it has a CRS attached to it, you can project it, you can manipulate it in any way, in the same way that you've manipulated any other object before. So if you had, say, this, and this is going to be live programming, so I'm not, things can go wrong, but what was the code for? Does anybody remember what the code was? Is what? 3.4. Somebody has the... Joris, do you remember the CRS 4 meters in Europe?
The one for Belgium, I know.
Which one? Yeah, that one.
3.1, 31, 7.
There you go.
No.
Nope.
4326.
Okay. Anybody has anything else? Oh, sorry. Actually, can anybody tell me what this error is? So, and this is really good. I run into this problem all the time, so I'll highlight here to hopefully save you some time. So if you look at the error, it says polygon object has no attribute to CRS. This is, so to CRS is a GeoPandas method, right? So it will only work on geoseries or geodata frames. Yeah? Shapely objects, I'm going to say this, don't have a CRS attached to it, right? They have coordinates, but they don't have a CRS attribute. That attribute comes on the geodata, on the GeoPandas object, whether it's GeoSeries or GeoData frame. And because of that, then the two CRS, the CRS conversion, all of that happens within GeoPandas.
So you want to stick your buffers in a data frame?
Yeah. So you can do, I told you live programming is never a good idea. There you go. Sorry, Joris, what was the Belgium one?
It is Turtran 370. Almost.
There you go. Okay, so what have I done here? This is the same buffer we had before in degrees, right? So the buffer we created in degrees. And then we stuff that into a GeoSeries, and we make sure we explicitly enter the CRS for the GeoSeries. And because it is unprojected, this is the same as the city's CRS. So you could specify in any way. Then once you have that GeoSeries, then you can use 2CRS to convert. We project it into the EPSG, which is expressed in meters. And then if we plot it, then we have this original buffer, which when you create it is a perfect circle. When you reproject it, is not necessarily the case, a perfect circle. Yeah, it's more of an ellipse. Any questions? No? All right. And, well, buffer is one. Once we have the buffer, as I said, the real power of all of this comes when you, these are all building blocks, right? This is like a Lego. Any Lego piece doesn't do anything. Is when you put it all together that makes a boat or a car or whatever you're trying to do. So the real power of these comes when you start combining, say, buffers with intersections, with unions, and so on. So the intersection, just a couple of examples to show you. It'll take all of the geographic objects you pass and return the intersection of everything, right? So everything, the area that is shared by all of the objects in the series you're passing. The union will pass all of the area that you're passing, will kind of put it into one. The difference will return the area that is not commonly shared, in this case between the buffer and the Belgian polygon. And as I said, this is just a couple of examples. There's a lot of other operations. I'll just tell you one final one that is particularly useful. This union, in many cases, in many cases, that's what you want. You have a bunch of polygons. You want to create one out of them that contains all of them. There is a difference between union and unary union, and I can't remember it now. But you want to use unary union. That's the lesson. So in this case, if you want to create a polygon, so say you have all of the African countries, and what you want at the end is a polygon of Africa, not a composite of different smaller polygons. So you start with African countries with just a simple querying, and then you call the unary union, and they'll give you a polygon that combines all of the geometries that you've passed in. Yeah? Any questions? So I have another quick example, but I think I'm gonna, in the sake of time, I'm gonna skip it because it's too easy for you guys. So I'm gonna move over to the last bit I wanted to cover, and then we'll continue. Any questions before this? Yeah.
These intersection union, they are in Shapely and GeoSpace.
So GeoPandas use, so the question is, does the intersection, union, difference, and so on is in Shapely and GeoPandas? The answer is the heavy lifting happens in Shapely, but you can access it through GeoPandas. So when you do same as we've done above with the intersects, contains, crosses, and so on, all of that really is shapely operations, which is to say that's really geos operations. So GeoPandas exposes them to you in an easy way to use with geodata frames and geoseries.
So if I wrap everything in GeoPandas?
Yeah. Yeah. More questions? Nope. All right. So then let's move on to the third notebook, the spatial joins, and hopefully I can get to that in 20 minutes or so. Okay, so before anything, let's import everything we'll need, data and libraries. Just a quick recap. So we're going to see here spatial joins. They're really, I mean, computationally they're very different, but conceptually they're very similar to non-spatial joins. So if you're familiar with pandas and with joining and merging data frames based on keywords, conceptually is the same idea. Is the idea of a spatial join is if you have two geodata frames or two tables that have some sort of geographic pinpointing that you can put on a map in some way, we're going to join them based on the location of their observations rather than the traditional keyword join. So here's a non-spatial example would be, let's pick up just a few cities, Bern in Switzerland, Brussels, London, Paris, and then manually, just for the sake of the example, let's add the countries that they're in. And then this is just a subset of our cities data frame. Yeah, nothing special. There's the name, there's the geometry, and then there's the country. And then let's also subset the countries just so we have two small, manageable kind of data frames that we can, at least I can directly relate to rather than 400 observations. That doesn't really mean much to me. So the idea of non-spatial joins is you have a table that has a column for a country, which is, for example, in the cities, you have a column that is the country where the city is, and then you have another table with information on countries. And as part of that table on countries, you have a key that is the country code. So if you have that common column in the two tables, you can join them together with the join or the merge commands. And there's nothing spatial. I mean, in this case, you're doing a spatial in the sense that you're joining cities to countries, but computationally you're not joining anything spatially. You're just saying, I know this table has a column that is shared with this other table, and then we're going to use that common keyword to join them. Yeah? And then what you end up here is with a merged table that has the data you had for the cities, so the name, the geometry, and the country code, and then to the right of that has been appended the information for the countries. Yeah? So again, nothing implicitly spatial in this join. Now, that is great when you do have the column in both tables, right? But that's not always the case in many cases, and that's one of the, to me, one of the key powers of space and geography is that you can use it as a kind of sort of common index that you can use to combine data without having that extra column. So how can we do that? GeoPandas has an S join, which plays on the join in pandas that does a spatial join. So in this case, where we have cities and countries, again, it's going back to the previous notebook of pointing polygon. Is the point within the polygon? Yes. If so, then I'm going to append all of the information in the polygon data to the points. Yeah? So again, we want to do that join without having to explicitly say, if we don't have that data, which country every city is. We're just going to, I mean, we have that information encoded in their location. So let's go ahead and run it. The way you do it is the S join tries to use as much of the join API in Pandas. So if you've played with that, a lot of it is similar. or tries to mimic that, translating it into the into geographic grammar, so to speak. So we're going to join cities, which is a bunch of points, with countries, which is a bunch of polygons. Then there's an op attribute for operation, and here all of the operations that we've looked at before, all of the spatial operations, so the within, the crosses, the intersects, touches, and so on applies. And then how, this is just traditional database jargon, right? So it's, and in this case we're saying left, so we're saying that the city's data frame is your reference table, and then to that you want to append the information in the one that's on the right, in the countries one. Yeah? Does this make sense? Cool. Oops. And then what do we end up with? We end up with a table that has all of the information that cities had and all of the information that countries has, and it's being joined by location. And because we use the within, we use every point will get the information of the polygon for which the point is within it, right? If that makes sense. Any questions?
Is there,
Yeah.
is there a way, let's say it wouldn't find, for one city, it wouldn't find a country to determine whether it keeps that city or not? We usually see that.
So the question is, what if there's a point that is not within any polygon?
Will it keep it in the geodata frame or will it throw it away?
So before I tell you a lie, yes. So that really depends on how you specify the how, right? So if you say left, it's going to keep every observation in the left, right? And if something on the left doesn't find a match in the right, it'll just throw a missing value for those rows. So it'll give you a row with all of the columns, but the columns that come from the right will be missing data. If you said inner, which is the default actually, what it would do is it would give you, it would give you just the subset that where everything is dense, so to speak. And if you said how right, it would keep everything on the right. Yeah, does that make sense?
Yes.
Any more? Yeah.
The resulting join data frame only has one geometry column, and what happened to that's for the city, I guess, right?
Yeah.
What happened to the geometry for the countries?
What happened in what? So the question is, on the join output has only one geometry, which in this case is the one for cities. What happened to the one of the countries? That gets discarded, and that is because by agreement, a geodata frame will only have one geometry column.
Is there any way to keep it? I mean, is there any way to have multiple geometries and geodata?
I don't know if there is technically, but you shouldn't. In the sense that the idea of a geodata frame is having one observation for a single geometric object. So if you wanted to have two, I think, and I guess yours will probably be better, but my view is if you want to have two observations, just make it two rows for every observation. Say if you have, imagine that you want to keep countries, and countries, you want to keep the polygon and the point of the capital. Then instead of having a row with two geometries, one for the polygon of the country and one for the point of the capital, you would do either two tables, as we've been doing here, or potentially you could consider having two rows, one for the country with the polygon and one for the country with the point of the capital. But by agreement, GeoPandas will only have one geometry per row. And this is kind of in agreement with how PostGIS works and so on. Yeah.
So I was just thinking, comparing that to an outer join canvas, where you could actually, I mean, you'd have missing values, right? The variable that didn't exist in the left and the right. But so I mean, I was thinking the analogy would be you'd have a could have two geometries, one with missing values. But no, that's not how you do it.
Sorry, what's the question?
So if you did an outer join
Yeah.
in regular pandas, right, where you have, you're doing a join, but you're missing, you have two different variables describing the same concept with different names. And if you would just have missing values.
Yeah. That would work the same here, though.
That would work the same here?
Yeah, so you could, it's another twist of the previous question, because you do have the how attribute, the how argument. You can say how outer, and then say, in this case, imagine there were some cities without a country and some countries without a city. It would still put them there. It's just that the row of cities without a country would have missing values on the country columns, and the countries without a city will have missing values on the city columns.
But you couldn't have two geometries with one geometry missing.
No, yes, it would only keep one.
It would only keep one.
I believe so. Yeah.
So then for some it would keep the geography of the city, and for those where the left was null, it would keep the geography for the country? Or would that be?
Actually, sorry, I'm wrong, and I just lied to you. There is no outer for that very reason. So, yeah. See, so you can do left, it'll keep your geometry on the left. You can do right, it'll keep your geometry on the right. Or you can do inner, and it'll use the intersection, but then will retain only the left, if that makes sense. There's no outer, sorry, I should have said. Any more questions? Okay, so then let's move on to the final one. There's a couple of exercises that I'm going to skip for time. So right now, spatial joins are really about combining data, but you don't modify geometries, right? With the spatial joins, you just have, say, points in polygon, you put them in relationship, but the output of that join is still the original geometries you're passing in. Sometimes that's what, I mean, in a lot of cases, that's what you want. In other cases, what you want actually is, through that operation, generate a new set of geometries. And this is equivalent. So the spatial join relates to the spatial relationships the way that spatial operations relate to the overlay, right? So if you want to do a combination that results in new geometries, you would want to use an overlay. And then you specify the spatial operations that you want to do with the how, again with the how argument. So let's say, for instance, that we want to get, we have the African countries, and then we draw a buffer around the cities. So let's say we're delimiting urban areas in Africa, and then what we really want to get is a map of the rural area. So all of the parts of Africa that are not within the area, within an urban area. So then we can call the overlay. We pass Africa as the polygons, cities, and then what do we want as the output? We want the difference of those two. Yeah? And then that's what the overlay returns. So again, just to reiterate, the spatial join combines information using location as the joining column, but it doesn't modify the geometries. The spatial overlay does modify the geometries, and you can use all of the spatial operations to modify those geometries and create combinations. Yeah? Any questions?
Can you just explain the buffer again, why it was required there?
So the idea, what do you mean why it was required here? So it was just the example I had was, let's say let's just keep Africa, this is our polygons, and then we have our cities. Our cities are points, right? And by definition, points have zero area, an area of zero. So because they don't have dimension, it's a single point. But let's say in the example I gave was, let's say that we want to keep the non-urban areas, so let's call the rural areas, so rural Africa. So how can we define that? Let's say we pick every city and then we define the urban area as a buffer around that point. So let's say in this case it was 2 degrees around the centroid. And then you're turning cities from points into polygons, circles, really. And that's what we were calling in this simple toy example urban areas. Then let's say, how do we get the rural areas? By getting all of the country minus the part of the country that is urban.
So the 2 of the buffer, there's a radius of the zone around the city point.
Yeah, which is this. And in this case, it's 2 because cities is expressed in latitude and longitude, and then it's degrees. But say if you projected it to something in meters, you could express that number would reflect meters, and you could say a buffer of 500 meters, a buffer of 1 kilometer. If you did say 1 kilometer, you will have to enter 1,000, but because it's always in the unit that the CRS is expressed. But yeah.
It looks like if you increase the buffers and you start getting overlaps between your buffers, it kind of cancels out the difference operation and starts including it again. Is there a way to account for that?
What do you mean?
That's a bug in GeoPandas, and it will be fixed in the next release that hopefully during the sprint will be released.
There you go.
Yeah,
that's an
the
answer.
operation currently has some, for those coordinate cases, some bugs.
What if you want the buffers to actually be unique for each city, like based on population or something like that? How would you go about creating that city's...
So the question is, how can you create tailored buffers to every city? In that case, the way I would do it is, I mean, this is again a good example of just combining different operations, right? So then I would probably end up doing. Well, I'll explain you, and then if I can live program it, or maybe I'll do it in the break because we're coming up to the time. But the idea would be you can use an apply function and then apply that row by row, and as part of that apply function, define the value you want. So you could, for instance, have a column, another column in every row. Say, imagine we had information on population for the cities. So then as part of that apply function, as part of that function you define to pass through apply, you could say then, I know that in this row there's going to be a pop column, use that and transform it in this way to come up with a radius. And then that radius, take it into the buffer, generate the buffer. So at that point, again, it's just more general Python programming rather than specific functionality that is. And I think that that's a feature, not a bug, really, because what GeoPandas is doing is making all of the geos operations Pythonic in a way that you can plug them in with the rest of your workflow. Yeah, does that make sense? So maybe on the break, I'll try to live code that, but I'm not going to embarrass myself. I'm not going to finish off with an embarrassment. So, any more questions on this? Yeah?
A more general question. How does GeoPandas relate to something like, so obviously this isn't open source, but with Esri ArcGIS software, is there any sort of relationship between...
Yeah, it does not touch.
It can't read any like geodatabases or anything like that?
Geodatabases...
GeoPandas reads everything that GDAL can read.
Yeah.
And GeoDatabase, I think GDAL
there is
has
a
some
driver.
support for it.
There is a driver, yeah, I think.
Yeah. So basically,
we can read actually
if
most.
GDAL can read it into a tabular format, and if it's tabular format and GDAL can read it, you can import it.
Except KML.
But it's because it's not a tabular format.
Oh, okay. Well, fair enough. Never try to comment on Joris. He always knows more. But yeah, I mean, basically, I don't think it operates in any way with ArcPy. It basically does, as far as I can tell, pretty much the same, or it's comparable, except it's based on a fully open source stack.
And if you compare it, for example, with QGIS,
yeah,
many of the operations you can do in QGIS, you can do in GeoPandas, and even many of the things are actually using the same libraries under the hood.
Yeah.
QGIS will also use GDAL and will also use Geos for certain things. They
Yeah.
also have their own custom algorithms implemented for many things, as does GeoPandas. But many of the core open source software stack in the Geos is common.
And I know it's sacrilege in this room, but if anyone uses R, the SF package is pretty much the same. It relies on geos for all of the geospatial operation. So at the end of the day, when you draw a buffer, whether you do it in R, in QGIS, or in GeoPandas, the heavy lifting is being done by the same code, which is geos. All right, so do we have a break or we switch?
Yeah, I think we should. Maybe just
Yeah, one more. I was gonna, before that, there is a set of exercises for these two notebooks on the same file that, okay, no. The case conflict file has a set of exercises.
Yeah, so you can always, because we had a bit too much material for the 2 hours.
Never say you're not
first
gonna
part.
end on an embarrassment.
So you can always continue there the exercises. It applies everything that Danny showed on that.
So everything from spatial operations on, and same as the previous session, the solutions are there. So if you get stuck, they're there.
Yeah. So this concludes the first part, which was really focused on getting to know GeoPandas. After the break, we will still use GeoPandas, but combined with many of the other data science, spatial data science tools that we will show you. So let's say
10, 15.
Yeah, 10, 15 minutes break.
What would people prefer, 10 or 15?
Right. We'll play 12.
So we should start? All right, welcome back. In the second half, I'm Serge. I think I introduced myself before. We're going to shift gears a little bit. So the first part was about geoprocessing, dealing with all the rich varieties of spatial data formats and coordinate systems, and geoprocessing, the spatial operations. We could call that deterministic spatial analysis. That is, you're interested in the spatial relationships between your observations. In the afternoon, we're going to switch to looking at methods of visualization of spatial data. There was some notebooks in the first part that we didn't get to. So we're visualizing spatial data with an eye towards exploring spatial data to identify interesting patterns, and then ultimately to modeling spatial data. So Levi will be covering some of the modeling capabilities. We're primarily going to be focusing on the library PySAL, Python Spatial Analysis Library, which started a long time ago before we had things like Shapely, before we had GeoPandas, before we had CartoPy. And we had to write, we, the people who work on PySAL, work in the area of spatial econometrics, spatial statistics, geocomputation. And we want to develop analytics that would sit on top of these very elegant and strong data processing, geoprocessing. But we didn't have them back in the day. So now we're very excited because we can focus more on the geoanalytics and then partner with GeoPandas and related. So we're at that part of the workflow, if you want to think about it in terms of a scientific workflow. I'm going to be focusing on notebooks 5 and 6, and then turn it over to Levi. So visualization is a massive area in scientific computing, but in geography in particular. I am not a cartographer. I'm more of a statistician, spatial statistician. So we're going to just delve into a little bit of cartographic theory here in terms of choropleth maps. Now, choro means region, right? So we have aerial unit data, polygons, that we want to understand how some spatial attribute, that is some substantive variable you're interested in studying. Most of our work is in the social sciences, so we could be looking at income levels or housing prices or market segmentation. And we have observations, could be polygons, could be points, and we have an attribute that we're measuring for each location. We want to understand the spatial distribution of those attribute values in space. We are going to look at two sets of methods that are complementarity. We're going to look at visualization methods, so mapping is very powerful, but we're also going to couple that with quantitative statistical measures to get at the same question, to try and understand the spatial distribution of these patterns. So choropleth mapping, the effectiveness of a choropleth map is largely a function of two things, okay? The first is given the distribution, the statistical distribution of the attribute that you're interested in, what is the appropriate classification scheme? This is essentially a one-dimensional clustering problem where you're trying to group observations based on their value similarity into mutually exclusive classes and maximize the difference between the classes. So you're trying to summarize the statistical distribution of the data. And there's an embarrassment of riches of classification methods, some of which we're going to look at shortly. So that's one half of the scissor. The other half of the scissor is the symbolization you're going to use once you've selected that classification scheme. And it's those two together that are going to drive how effective your visualization is. And by effectiveness here, that depends on the context. So it could be you're a scientist trying to explore your data, understand the spatial distribution. In other cases, it could be you're interested in identifying outliers in the data from a spatial perspective or from a value perspective, or some combination of these approaches. So this notebook, we're going to look at how we carry out map classification, ultimately then to build a choropleth map. So classification first, you have we're going to work with a data set from Berlin. So we're using GeoPandas to read in the data. And the data, this is from a workshop we gave in Basel a couple months ago, where we talked about how you download the data, construct the data, do aggregation from points to polygons. So these are Airbnb listings that we're going to aggregate to polygons, i.e. neighborhoods in Berlin. So that's the data set we're working with. We can point you to the older notebooks that build the data set and use some of the functionality Danny and Juris covered this morning. So the variable we're interested in here is the median price. Is the font big enough for people in the back? Make it bigger? Okay. Okay, so we have median price, and this is the median price of all the listings in a given district. Right? We're looking at the top 5, or the first 5 districts in the data frame here. Okay, so that's the variable of interest. I could be an urban economist interested in how the housing market functions in Berlin. So we're first going to understand the statistical distribution of those values, abstracted from geographical space. So this is the median price, and I think it's in euros per evening. The variable of interest. So the observations are taken for each of the districts, and here we're summarizing the value distribution. There's no geography here. The space, if you will, is the value of the attribute, the median price. Okay, and it's a little bit of skewed distribution, not atypical for income data or dollar-denominated data. You have a couple of very high price listings, and you see where the center of the distribution is, off to the left here. All right. So we're using Seaborn there just to visualize the data. We'll throw in a rug plot that shows you the locations of the individual values at the bottom there on the price scale. Okay? So that gives you a sense for the statistical distribution of the values. Ultimately here, we're going to be interested in how those values are distributed in geographical space in the city of Berlin across these polygons, which are the districts or the neighborhoods. And to get at that, we're going to back up with the plot method for the geodata frames using the defaults. So to do a choropleth map in GeoPandas, we have the data frame, which we've created. We know how to do that. We've done it this morning. We pass in a column argument for which attribute do we want to plot. And it's the median price. And we get default color scheme and default classification, which we don't know what they are yet. We're going to get into this. Okay, so that's a view of the spatial distribution of the median prices. Anyone from Berlin? Okay, so I won't get called out here for not knowing anything about Berlin. Okay, so maps are very powerful because they tap into the way our brains work in terms of we are pattern recognizing animals. We wouldn't be here if our ancestors weren't pattern recognizing animals. So effective map design is about tapping into the way our brains work. But you can make an argument that we're perhaps too good at pattern recognition in that we can pick up on false positives, things that we think are there, but they're actually not there because of the way the implementation of the visualization was done. And there's a couple of dimensions that complicate things for real-world maps. These polygons are not all the same size, nor are they the same shape, right? And larger shapes tend to dominate our cognitive load, so to speak, so we're drawn to them. And that makes it difficult because from a statistical perspective, each one of these observations should have equal weight. But when we put that on a map, things get much more complicated, okay? So let's peek in under the hood a little bit and try and understand what's going on. We're going to, number one, make the map a little bit bigger. So the default, I believe, for the first map that we saw was to use quintiles for the classification. So we take the housing values, we sort them from lowest to highest, and we break them into 5 equal-sized groups. And then we assign a color hue to each of the groups using a sequential hue so that we get the impression of where the high values are and where the low values are. All right, so we're doing that again here. We're being explicit. So the scheme is the classification scheme. And that comes from PySAL. There's, that Pandas has a wrapper around to use several of the classification schemes in PySAL. Not all of them for having to do with the complexity of the function signatures, but this is the default that we saw earlier, just making it bigger here. All right. So we bumped up the size of the map. We made it explicit for our classification scheme. And we can get increasing granularity. So now we're going to add a legend. So we see what the breaks are for the different bins according to this quantization of the attribute. Okay, so the darker colors are for the lower values of the rents. The lighter hues are for the higher income, or sorry, higher valued rents. Questions so far? All right. So the default's quantiles. We could do quartiles by just changing the argument k to 4. And instead of splitting into fifths, we're splitting into quarters based on the value distribution. All right, and you can change that to whatever you want. Octiles, deciles, by just manipulating k. So the classification scheme is important, but also the color ramp that you use. And there's a lot of interest in color ramps and visualization. Color Brewer, which comes from Cindy Brewer. She was a colleague of mine a long time ago at San Diego State. She has a very effective website for helping you decide what color scheme to use for a choropleth map, depending on if your attribute is quantitative or categorical. Is it a diverging value distribution and so on? And what is your intended medium? Are you going to print a hard copy map? Are you going to put it on a beamer? So it's an excellent tool. And many of the libraries in the Python world have already pulled into Color Brewer and then extended it with other things like Palatable and so on. So we just change the color scheme here, keep the number of classes constant. So we can first look at, okay, what's the impact of the choice of the color scheme for the ramp? All right, the default versus orange to red or green to blue. Remember, it's the same attribute, just that one dimension of this symbolization changes. Alternatively, we could change the classification scheme. And we're going to get into these in a second. So we could use quartiles or equal interval or an optimization approach, Fisher-Jenks. Again, same collection of values for the neighborhoods, but the classification scheme differs. And then obviously you could change both the color scheme and the classification scheme. Okay, so GeoPandas supports the classifiers in PySAL that have a common signature. That is, they typically take k, the number of classes that you want to define, right? But there are other classifiers in PySAL. So there's a package in PySAL called map classify that just does the classification. It doesn't do the visualization. That's not the goal. The goal is to make it quick and easy to get different classifiers. And then you can couple them with whatever you want, CartoPy, GeoPandas, Folium, and so on. So the classifiers that we have in map classify: box plot, equal interval, Fisher-Jenks, sampling, which is for large problems, head-tail breaks, and we're gonna look at a couple of these. Have people encountered map classifiers before? Is this new to most of you? Okay, so we'll do a little bit of a slower pace than I was planning on. Okay, so equal intervals, the first one we're looking at here. This takes the minimum value in the data set, the maximum value of the data set, and asks the user, how many classes do you want? In this case, I said 5. And then what it's going to do is subdivide that range into 5 equally spaced, equally width intervals. Okay? And so we call the equal interval class. We pass the attribute y, which is our income, the housing values, and k. And what we get back is an instance of our classifier object. And its repr is just the classification scheme. Okay, so you see that we have 5 classes. You have the upper and lower bound for each of the classes. And you have the count of the number of observations that fall in each of the classes. So this is purely based on the value distribution. There's no geography here. There's other attributes for the classifier object. So YB means the bin. Y is bin, so it's similar to a label in scikit-learn if you're doing clustering. It tells you which of those bins is each of the observations falling into. Second classifier, which was the default in the plot for choropleth and geopandas, is the quantiles. So same type of signature, you pass in the attribute, y, and the number of classes. Same repr. So quantiles, this is quintiles, we have 5. If you squint at the screen, the idea behind quintiles is unlike equal intervals, where the widths are the same across the classes. Here, the number of observations in each of the classes should be the same, equal count, all right? But what do we see here? Do we have equal count? Which class has the most observations? The first one has 39 observations, right? Which is more than 1/5 of the observations. And this is a common problem when you're doing choropleth mapping with values where you have a lot of duplicates, a lot of ties, right? So for quintiles, in this case, you sort the data and you find the 20th percentile. Right? Now, if you have a lot of low values or a lot of values that are duplicates, you could have that be, say, I don't know, 32 euros. But if you have 100 neighborhoods that have 32, then you have a problem. Because if you rank the data, you have ties, right? And this is inconsistent across all mapping packages, how they deal with the ties, what you do. So what we do is we just bump it up to get the ties, and then if the tie was, say, at 32, and we had 132, we move the bottom of the first quintile to the 100th ranked observation, okay? At least we tell you what we do. Other packages don't tell you. You have to guess. All right. So Y bins. And there you see that there's only 57 unique values in the attribute distribution. And that causes problems for quantile classifiers. All right, so how do you decide which classifier to use? Well, it depends on what your objective is, and there's different objective functions. So one that's built into the classifier is a measure of fit, and this is like trying to come up with a good clustering solution. This is absolute deviation around the class medians. And we're going to compare 4 different classifiers for the same number of classes, so 5 classes. And I want to maximize the internal homogeneity of the classes and maximize the external heterogeneity. I want the differences between things belonging to different groups to be as large as possible, and the differences between things that belong to the same class small as possible. So lower values is better for this, and we see that the Fisher-Jenks class has the lowest fit. It's guaranteed to. Okay, so, but fit is not necessarily always the ultimate objective here. Why not? Well, there's classifiers that are used to detect outliers in the data, so extreme values, and those extreme values could be errant observations, data errors, or they could actually be interesting true values that you want to flag. There's two classifiers you could use for this purpose, standard deviation and mean, where for the standard deviation, you define the classes based on distance from the mean and multiples of the standard deviation. Okay, so you're getting out in the tails explicitly, or a box plot, and we'll see images of box plots later. But the idea here is you have the 50th percentile of the data from the 25th percentile to the 75th in the core of the data set, and then you have things called whiskers and fences that are going to help us bound outliers. It'll be clear when we get back to the visualizing the maps. Okay, so using these classifiers in GeoPandas for the classifiers that are not built into GeoPandas, you can do that. So if we wanted to do the box plot classifier to identify outliers with GeoPandas, this one's not by default, so you have to sort of build it in. So first we're going to have a simple list with the legends for our label. So a label of 0 means you're a lower outlier, you're a low extreme value. 1 means you're low whisker, so you're on the whisker of the box plot. Q2 and Q3 are the 25th to 50th and 50th to 75th percentile, so they're sort of central observations, they're not extreme. And then we have the high whisker in the box plot and high outliers. So those are our legends for our label. Then we loop over our box plot classifier and we extract the bin label, which label is each observation in. And then we're going to use that list and attach it to the data frame as a new column in the data frame. Right? And then plot that because GeoPandas can support that. We just treat it as a categorical data type in GeoPandas, and then we can exploit the plotting function. Okay, so then we don't have any low whiskers, so there's no low extreme values, but we do have a couple of high outliers. Right? And the high outliers here, they are more than 1.5 times the interquartile range above the 75th percentile. So these are the really extreme high value neighborhoods or high rent neighborhoods. All right, and so now we're seeing that we're pairing the statistical distribution with its articulation in space, in geographical space. Okay? Questions on the classifiers? Is that fairly straightforward? Gives us different ways to group the data. And then we pair that with the plotting function GeoPandas to do a choropleth map. No questions on that? Fairly straightforward?
We don't have a low outlier.
We do not have a low outlier in this case. Yeah. Right. Right. I teach a 15-week course on geovisualization, so we spend a lot of time on classifiers. So we're getting a thumbnail sketch here. Yes.
So just curious on the like on the quartiles, you know, that's pretty easy math to divide up what goes where. Would you ever have any custom clustering normals on your legend? You know, like as a human eyeball, you might say, oh, these all look similar, and then here's a couple of other peaks.
Yeah.
That might be a little bit more difficult if you separate those.
Yeah, we did Fisher-Jenks, which is an optimal classifier. That'll do better than we can do by eye. We also support user-defined classifiers, so, well, not classifiers, but bins. So if you wanted to pre-specify where you wanted the breaks to be, you pass that into the classifier, and it'll return an object that then has all the functionality. Yeah. Other questions? Okay, so now we're visualizing the data, and as I said, our brains are really powerful pattern detectors, but sometimes we could fool ourselves and find, apparitions. So people seeing Jesus in the toast kind of thing. This is a demonstrated phenomena. There's a lot of literature in psychology about our pattern recognition because we have to survive. So we're trained to identify things that might eat us or kill us, right? So now we're going to couple the visualizations with statistical tests so we don't fool ourselves. All right? And this gets in the notion of spatial autocorrelation. So it's autocorrelation. We know what correlation is, right? You have two variables, and you want to see if they're positively correlated. That is, when one is high, is the other one high? When one is low, is the other one low? Or are they negatively correlated? Is there an inverse relationship? So that's correlation. Auto here is that we're looking at one variable. In this case, the housing prices. And we're going to be interested in the question of whether the value in one neighborhood is related to the values in the nearby neighborhoods. Okay, so it's autocorrelation because it's a single variable, but it's still going to be a form of autocorrelation, of correlation. So we're using the same data, same plot from before. And what we do with autocorrelation, first we're going to start with what's known as global autocorrelation. And we're going to pair two types of similarity together. The first is value similarity. So we want to understand how far apart things are in attribute space, in the value of attribute space. So high rents are far away from low rents, okay? And close rents are close. But we want to couple that with the notion of geographical similarity, right? So how we express that gets into a large literature. We're going to use what are known as spatial weights that define neighbors. So they're similar to like an adjacency matrix for network analysis, if those of you took any of the network tutorials. All right, spatial weights are very similar. They have a similar mathematical representation. But our spatial weight here, you can define it in many different ways, neighbors. We're going to use simple contiguity, which is going to leverage some of the geoprocessing we saw this morning. And we're going to define neighboring districts as though that share a vertex or an edge on their polygon borders. And from that, we're going to construct from PySAL a queen contiguity structure. That is, if any two polygons share at least one vertex, they're neighbors. Okay, now we're reading a data frame here. So we're peeking into that geometry column and running an algorithm that detects the topology. Okay, so our queen W is telling us who is a neighbor of who. And that's our geographical similarity. You can think of this as a matrix, although it's not a matrix. Each row tells us for polygon 0 who its neighbors are. There's non-zero values in that row, in this case ones, where we have a neighbor between column or row I and neighborhood J. If they're not neighbors, it's a 0. We're going to transform those ones to be row standardized so that now if we summed across the row, the value would be 1. So the weights get row normalized. That's what we're doing here. We use the weights, the Wij's, to develop a weighted average of the attribute values in the local context. That is, for a given district, we now know what the neighboring districts are, so we need an average of the housing values in that neighborhood, and that's the operation. That's where the spatial weights come in. So it's simply a weighted average of the values for the neighbors. And it's this variable called the spatial lag, which we're going to then correlate with the original housing price. So it is, in fact, a correlation. We've just constructed a spatially explicit variable that captures local context. And so we correlate them ultimately. So that's our spatial lag. And we can plot it. It's like a smoother for those of you who do remote sensing in a sense, but this is not a pixel image, right? These are irregular polygons. So this tells us about what's going on around a focal polygon, right? But it's the value in the polygon. So it's looking at information in my neighborhood and bringing it back into my neighborhood. And what we're interested in now is these two maps. The original price is on the left. That's the quintile map. And the spatial lag is on the right. So now we want to explore the correlation between those two maps. So it's a bivariate correlation in a sense. This is also another course, 15 weeks of spatial statistics. So we're going to do a quick dive here. So are these correlated or not? This is not a scatter plot. This is very complex visually to get at. Okay, so we're going to use statistics to get at this. And we're going to back up and make it simpler to develop our notion of why these statistics work. Instead of having 5 classes, we're going to have a black and white map, high values and low values. So we're going to convert our binary, we're going to convert our housing values to high and low. Here. And then I'm going to plot that map. to reduce the cognitive load. So the dark polygons, black, are above the mean housing price or rent, white are low. And now we're interested in the question of if those black polygons are randomly distributed in space, and conversely, are the white polygons randomly distributed in space, or is there some structure there, right? And we're going to come up with statistical tests to answer that question. The oldest tests are called join counts. So is that map random or not? That's our question. Our null hypothesis is that if we had, say, 68 black polygons and you randomly assign them on the map, what would the map look like if there's no structure in the process generating the data? So we need a test against that hypothesis. So join counts work with joins. And all a join is when you have a pair of neighboring polygons. And we know how many neighbors there are because that comes from our W. So for each join, we then ask, well, what type of join is it? Is it a poor neighborhood next to a poor neighborhood? Or a low-low? Or white-white? Or is it a rich neighborhood next to a rich neighborhood? Dark-dark, black-black? Or is it heterogeneous? White next to black or black next to white? So there's only these three types of joins possible. Black-black, white-white, or black-white. And join counts, we're going to count up how many of those different types of joins did we get in our actual data versus some reference distribution under the null that whatever governs housing markets in Berlin is random spatially. Okay, questions on those concepts? Okay, so we need to count the joins. And in PySAL, we have an ESDA module for exploratory spatial data analysis. It uses our W object together with our binary attribute. So join counts, you pass in the YB, which is the binary valued attribute, and our spatial weights. And then it creates an instance of our JC object. Found out that there was 121 black-black joins on the actual map. 114 black-white, and 150 black-white. And that's it. That they're going to exhaust the number of joins. The number of joins is an attribute of the spatial weights because it's a binary weights matrix. So it tells us how many neighboring pairs are there, and there's 385. So now we're back to the question. If you had 6 to 8 black cells and that spatial structure for the joins, what we would expect for where those 6 to 8 black cells would be co-located or not co-located. How many did we get? We actually got 121, but we need a reference distribution, all right, to decide if that count is higher or lower than what we would expect under the null. And in PySAL, there's two ways to get a reference distribution. There's analytically, statisticians have derived what the distribution should be. So it's like looking up in the back of a stats book and comparing your value to a table. But they don't work so well because every map is different. They're not regular lattices. We have different geometries. So instead, we rely on computationally based inference. We're going to play creator of the universe and simulate the null hypothesis by taking up the actual housing values and shuffling them around the map randomly, right? Because that's the null. The null is that there's no spatial structure. We create one synthetic map. We recalculate our statistic. So now we have two values for our statistic, our observed value and this one from the synthetic map. This is called a permutation of the values. We repeat this, say, 1,000 times or 10,000 times, depending on how much you want to do. And for each one of those, we have a draw from the null distribution. And from that, we collect all these, and we compare our observed value against the null to decide if it's significant or not. And it's a pseudo-significant value. So we do that when we create the instance of the join count. On average, for the fake maps, you should have got 99 black-black joins. That's the average. But we have all those synthetic joins, so if we do a kernel of the null values, that's the blue kernel, that's what to expect under the universe where housing markets are random spatially. There's no housing markets that are random spatially in the world that we know of. So this is not a surprise. But how extreme is our observed value? Well, that's the red, that's the value indicated by the red line. So way out in the tail. In fact, none of the values from the fake maps were as extreme as what we observed. Right, so it's highly autocorrelated data here. Right, there's strong spatial structure there. And hopefully you get a sense that this is a very nice complementarity to the visualization of the map pattern. Because map patterns are complex to process. All right, so that's our pseudo p-value. That's one of the attributes that's calculated. And it's simply the number that were as extreme or plus the one that we got, because we pretend like ours came from the null, divided by the number of permutations. I think it was at 999, plus the one we had. That's all that value is, the p-value. Well, we threw away a lot of information when we did the binary conversion. But that was just to try and develop our intuition of how the autocorrelation test, the logic of the autocorrelation test. So did that sink in? I know it's compressed. There's an industry of autocorrelation tests. There's new ones coming out all the time for spatial autocorrelation. We're going to look at, well, what if you kept it in continuous space? So now we'll look at a test for the actual values, not the binary values. It's called a Moran's eye for the guy who invented it. Moran was a statistician. Same idea. You pass in the value array, y, and your spatial weights, and you get back an instance of Moran's eye. Had a observed value of 0.09. Is that large or not? We don't know. We need a reference distribution to compare it against. And again, there's two ways. There's analytical, theoretically, and then computationally based. So we're going to show the computationally based one here. And for the continuous value, it's slightly different. So the synthetic p-value is still below 5%, which is your conventional cutoff for a significant statistic. So this is almost 2%. It's not as extreme as the binary case. But remember, for the binary case, we threw away a lot of information. We reduce a lot of the variation in the data, because all the high values are treated equally, even though we know there's some very extreme high values. This, we're retaining the full range of the values. Okay, so it's still significant. And then lastly, to finish off this section on autocorrelation test, these two tests were global. They answer the question about the map as a whole. Is that map random or is it not random? Yes or no, but we have a quantification of that. There's a newer set of literature on what are called local spatial statistics. And here, these local statistics are designed to identify the locations that are perhaps driving the overall pattern, or that deviate from the overall pattern, or spatial outliers. So we get into notions of identifying hot spots and cold spots. And we're going to do the same thing here. This is a scatter plot, which shows us on the x-axis, this is the housing price for a given neighborhood on x. On y, it's the housing price for the spatial lag, the weighted average in the neighborhood, of that neighborhood. All right, so the weighted average in the neighborhoods surrounding a district. And so the scatter plot lets us think about different types of spatial association, local spatial association. So if we think about the vertical bar, to the right of that, those are above average rent districts. To the left, those are the low rent districts. But what about the y-axis? The above are high neighborhood values, so high values in the neighborhood, below neighborhoods that are lower value surrounding me. So we put the two together, we have 4 quadrants. If we're up here, what's this neighborhood? What can we say about that neighborhood? Is it high or low? High. And what about the markets surrounding it? They're also high. So it's a high, high location in quadrant 1. Quadrant 2, mathematicians go counterclockwise. Don't ask me why. Quadrant 2, what do we know about this neighborhood? Is it above or below the average? It's below, right? It's to the left. And what about its neighbors? Those are high, right? So this is low surrounded by high, sort of the donut, hole in the middle, good stuff on the outside of the donut. Down here in quadrant 3, these are low, low, right? So these are areas where you have low housing values surrounded by neighborhoods with low housing values. And then finally, quadrant 4, high values surrounded by low values. Right? So these are like diamonds in the rough. So we have different types of spatial association here. In quadrant 1 and quadrant 3, we have positive spatial association, or value similarity in space. You have a high value next to a high value, quadrant 1, or low value next to low value in quadrant 3. That's positive association. Negative association is quadrants 2 and 4. Low value surrounded by high values, or high values surrounded by low values. All of those are different types of spatial association. If there was randomness on the map, these points would be randomly distributed across these 4 quadrants, but they're not, right? They're concentrated in 1 and 3, and the slope of that line is Moran's I, that global statistic. So our local statistics now, the first one, instead of having one statistic for the whole map, now we have a statistic for each location. And it tells us multiple things. The first thing, the Q attribute, tells us which quadrant is that statistic in. Is it 1, 2, 3, or 4? Okay, in the scatter plot. And then we're going to test if each one is significant or not, using permutations, but now it's more complex for technical reasons. We have to hold that location fixed and permute the complement set, because you can't be your own neighbor, unfortunately. Otherwise, you would inflate the spatial dependence, which means if we do 10,000 permutations, we have to do 10,000 different permutations for each location, one set for each location. And then we can map these. So now we're going to map those locations that were in quadrant 1 in the scatter plot that were statistically significant. That is, there's something going on with that location and its neighbors. They're both coincidentally high. Not coincidentally, but they're coincident in space. All right, and where are they? They're in the center of the city in this case. So those are our hotspots. The other ones are not significant. Okay, so we're treating them as we don't care. We just want to find out where the hotspots are for the market in this case. The other types of spatial association are the cold spots. So the cold spots are those, again, that were in quadrant 3, but were statistically significant. And we plot those, their locations. And then finally, we can do it with the outliers. So I'm going to jump to the final map here. So the outliers were in quadrants 2, which are the donuts, and quadrant 3, the diamonds in the rough. So this gives you a view of the spatial distribution of the housing values from a spatially explicit perspective, because now we've coupled these quantitative summaries of local spatial association together with the actual geography of Berlin. Okay? So this is exploratory set of methods. This leads to questions about why this map is like it is. The job of these methods is to raise those questions. The job of these methods is not to answer these questions. They're exploratory methods, right? So they're fitting in that part of the spatial analytical workflow. Okay, questions on these?
So the way you're testing for statistical significance of local hotspots is you're basically permuting randomly how are you doing that exactly?
Okay, so for this guy right here, this polygon, we know how many neighbors it has. So it might have 6 neighbors. So actually what we do is we take the set of values except that one. We randomly select 6 from that set. And we recalculate its local statistic.
And you do that over and over again, and then you just find out which is in the, whether or not it's in the 5 or 10%.
Yeah, essentially, yeah. You find out how many of the synthetic ones are more extreme than what we observed.
Okay, great, thank you.
Okay. All right, and then Levi's going to turn to the, well, I'll let him talk about what he's going to turn to.
So I figure we've got about an hour left, and we've got, by the way, my name is Levi Wolf. I'm an assistant professor at the University of Bristol. And so we've got essentially 3 notebooks left. One of them is sort of a problem set based on the local autocorrelation stuff that we just did. That would give you more of a sort of hands-on sense for how these things work, what it means when you detect a cluster, and sort of subjectively how to connect that to what that means in your own maps. Would you like to do that, or would you rather move on to regression and clustering? I guess, problem set, raise your hand. Well, a couple. Let's do the problem set. Because the only people who voted. Oh, okay. No problem set? Raise your hand. Okay, quite a few. Okay. Well, then let's move past that then. If you want to check that out, it's the case Ginny in a bottle, the Trump vote. It's on the relationship between economic inequality and the change in vote from Obama to Trump. Kind of some interesting stuff there that you can find in the local structure of vote by county. So the first thing that we're going to do is we're going to move onto the regression notebook. So this is notebook number 7. When we're talking about how to use geography in data science applications, you can sort of think of it most commonly in most useful applications as a data borrowing technique. So when Serge was talking about the spatial lag, right, what we're doing is we're constructing a new feature that gives us the average of a particular feature in the area surrounding every single observation, right? So if I have spatial data and I come up with some way to build a weights matrix, right? A weights matrix for what we were talking about before is like an adjacency matrix kind of for the graph of connectivity between the polygons. You can have this for point data, which we'll be doing here in a second. But if you come up with a way to express all of these spatial relationships at once, and you come up with a way to compute these neighborhood averages, you can use them quite often to do data science as synthetic data, right? But in reality, what we're doing is we're using geography as an instrument to give us additional features. We would call this, in other contexts, feature engineering. So here I'm going to import a couple packages that we're going to be using, and we're going to read in the same Airbnb data that we saw from the other notebook. But this time, we're going to also get information about the Airbnb prices at point level. So this is a collection of, I think, about 14,000 prices of Airbnb listings in Berlin. So these are nightly listing prices. So every night, some of these may have different minimums, so implicitly they're priced slightly differently. So if this were sort of a full analysis, you'd have to take into account a couple of different things. But in general, this is the spatial distribution of our prices in the neighborhood. And then let's, or across these residential districts. And then let's construct, actually, let's leave it like that. So the first thing that we'll do is conduct a kernel regression, right? So some of you may be aware of what a kernel regression does. Oh, do you have a question? No? Okay. Classically speaking, how kernel regression works is in feature space, you sort of, usually it's used in classification. You may hear about voting classification algorithms or things like that. Essentially what you're doing is, given a new observation, you try and figure out which class that observation is a member of by looking at an adjacent number or a distance decay radius of nearby observations in feature space, so in the multi-dimensional space of features that you have. And you're sort of taking the neighbor that all of the people agree based on their class. So if I'm a new observation and most of my neighbors are in class 2, then you would predict that I am also in class 2. That's kind of, in general, how these kernel regression ideas work. So that's in a classification context. In a prediction context, you'd sort of take the neighborhood average. So we would take, if I got a new Airbnb listing, I might predict its price to be the average of its 10 nearest listings. And so scikit does this stuff inside of the kernel regression framework, and we'll talk about that in a second. But here I'm going to pull out some data that's relevant to what we might think the price of an Airbnb should be. We have the number of people that the Airbnb says that it accommodates. So this is where the host says, you know, this can sleep about 6 people across 3 beds or whatever. You've got the full rating of the listing itself. So we call this the review scores rating. We've got the number of bedrooms in the listing, the number of bathrooms in the listing, the number of beds in the listing, the actual price, and then the geometry. So I'm just extracting this from the original, the listing data frame, which has a ton more information than what we need. And then here I'm going to structure sort of like a regressive framework where I've got some predictor variables, and then I'm trying to predict price of the Airbnb listing. And here I'm just, again, extracting this all from the data frame so we can work with it in shorthand. The last thing I'm going to do is I'm going to pull out the coordinates of all of the Airbnb listings from our data frame. And I'm going to do this by going through every single row of the data frame and pulling out its XY coordinates, stacking it into an array, and then stacking that whole thing together itself as an array. So coordinates now is just an NumPy array full of projected data. This happens to be in Web Mercator, which is accurate enough for the scale of computations that we're doing here. So here now I've got this NumPy array of XY coordinates, which we'll use to conduct these regressions. So the easiest sort of fundamental neighbor regressions that you can use are in the scikit-learn neighbors module. And this has a bunch of functions that some of them operate similar to the PySAL weighting functions for spatial weights. Ours tend to be a little bit more geographically focused, whereas the KNN stuff and, well, the neighbor stuff in scikit tends to be a lot more general for feature space stuff. But then we're just going to split our data into some training and some testing stuff for trying to predict these Airbnb neighborhoods. And then I'm going to do 3 different things down here. If you look at this next cell, I'm going to fit 3 different neighbor regressions. The first one is what I'm calling the spatial neighbor regression. So what this does is it only looks at the prices of Airbnbs that we observe, and it tries to predict what or it will eventually, it will try and predict the price of any testing data based on the closest elements inside of our training data. Does that make sense? So we're just using basic spatial distance, inverse distance weighted, as a way to predict our holdout set. So you could do this for any kind of feature data that you want to train a model on. You could see whether or not it holds. You could, do all sorts of hyperparameter optimization on this. Some cities may have different urban structures, so you have to use what are called anisotropic distance measures, which depend on the angle at which observations are related to one another. Then we're going to check this against an attribute version. And the attribute version is going to pick prices from our training set again, but it's going to try and use these exogenous regressors. So these additional informations that we have about our Airbnbs, the accommodation, the number of beds, that kind of stuff. It's sort of a more classic framework we're going to try there. And then we're going to try and mix these 2 things together. We're going to try and give an information about, we're going to try and make predictions about Airbnbs just naively using the spatial coordinates of the longitude and latitude as features themselves. Okay, so there's 3 models here that we're about to fit. It's a spatial one, which is just doing basic surface interpolation. There's sort of what you would consider a more classical regression, which is using nearby features to predict nearby output. And then we're using a hybrid version of that. Then we're going to make our predictions. What's up? Oh, yeah.
Is there a reason why you declared the k-nearest neighbors regressor 3 times? Or would that just need to be declared once and you could shoot it into the 3 models? Or?
I'm pretty sure you don't have to declare that 3 times. I just did it for assuredness. I mean, the initialization of a scikit estimator is pretty cheap. So in this case, so it's you can change that as you want. So then we're going to predict all of these values based on what we've got. So we're trying to predict, the spatial prediction is only going to use the coordinates of our observations to try and predict prices. The attribute-based version is going to try and predict prices based on the nearest exogenous information that we have. So using our X matrix, using the information on, accommodates or things like that, we're going to pick the other ones that are nearest to the holdout set in the feature space. There's no information about geography at all. It's only nearest in terms of most similar in observed attribute. And then finally, we're going to fit what I'm calling this sort of hybrid model, which uses latitude and longitude as themselves part of the attribute set. Now, when you look at the accuracy of these things, you see that the spatial model has about 10% of variance explained. So just by using the outcome itself, not including any of our exogenous regressors, we get an explained variance score of about 10%. Our exogenous regressor model, the one that uses the X information, which could potentially be a huge amount of X information, attains about a 33%. And finally, when you mix both of them together naively, you absolutely tank your model score. So what this is supposed to show you is that if you do want to try and use spatial data, you have to be careful about how you include it. Oftentimes, it's not going to be sufficient just to include a naive longitude and latitude into your data. You should try and use these concepts that we're teaching you, such as the spatial lag, using neighborhood averages as engineered features rather than just naively including information about spatial position. Does that make sense? Cool. Are there any questions just on this little example here? Does anyone want to see any alternative reconfigurations or refits? Yeah? I believe that I'm splitting into, yeah, I think I'm only holding out 2,000 observations or so that can change. The other thing is we don't necessarily know, I haven't ensured that the holdout set is spatially random. So it could be that there's spatial structure in the holdout set that affects our prediction accuracy. We're not going to talk about that, but all that kind of stuff can be assessed using local statistical techniques and things we discussed previously. All of that exploratory data analysis stuff applies to any type of spatial data. You just have to figure out how to express the topology. So yeah, I think we're only holding about like 2,000 out. Are there any other questions on this just basic example here? None? Okay. So what I would suggest then, if you're interested in looking at these kinds of kernel-based regressions for local data, there's a package in the analytic library that we work on called GWR. And GWR stands for geographically weighted regression. Geographically weighted regression is kind of like a mixture of these two concepts of feature space regression and spatial regression. In essence, what it's doing is it's fitting models at each site. If you've ever heard of Kriging or you've ever heard of spatial differential process models, these are all sort of a family of local smoothing models that all work in a sort of similar way. This one is a generalized additive model that uses spatial position to localize predictions and estimates. So the second thing we're going to do is I'm going to show you how to use this spatial lag / data borrowing technique in a more classical regression setup. So we're not going to use this KNN regressing kind of stuff. So here, I need to do some conditioning on our weights matrix because by default, if we construct a spatial kernel weight, it fills the diagonal with ones, and we want to make sure that we fill the diagonal with zeros so that our focal observation does not contribute anything to its estimate of the surrounding averages. So here, I'm going to fit that kernel weight, which is just going to apply a Gaussian kernel to every observation. It's going to adapt the bandwidth to ensure that a particular k-nearest neighbor criterion is satisfied. So I believe we include a whole notebook that goes way in depth on these weights matrices and how to model sort of spatial relationships specifically. But here I'm just using this to provide. It takes a while? Oh, bummer. K is 100. Okay, well. So the point of doing this here, in the same way that in the previous notebook we constructed an adjacency graph using the Queen's weight criteria, this is going to give us a sort of weighted, a way to construct a spatially weighted average of the nearest 100 observations that we have in our data set. So using this kernel weights, it's kind of like if you've used PostGIS or something like that, when you're doing spatial indexing queries, what these weights objects represent sort of conceptually is the output of an all pairs spatial relationship query. And we do this one time ahead of computation so that we don't have to do it later when we're running the techniques. It allows us to express everything in terms of matrix and linear algebra rather than needing to express it in sort of query language like PostGIS usually uses. So now I've run this weighting function. We've got a kernel weight, which gives us a Gaussian kernel centered on every single Airbnb that gives us a distance decay based on the Gaussian radial basis function based on the geographic distance away from that observation. So this is just an arbitrary way that I can say this observation is related to this observation by this spatial kernel. Y'all have seen heat maps before. This probably is somewhat familiar. Now, our data matrix, remember, is all of this data. Accommodates review scores, bedrooms, bathrooms, and beds. So that kernel weights matrix is in general just an n by n matrix that has been sort of specially constructed to give us certain attributes. So when I compute this wx, I'm pre-multiplying that matrix by my data matrix. And that will give me a new data matrix, which gives us the neighborhood average of every column in our original neighborhood matrix. So this stuff scales usually pretty well. If I can get that weighting matrix, I can use it as a filter to construct spatial averages. So now, if I look at wx, the matrix, it's a NumPy array. But it's a NumPy array which reflects a weighted summary of all of the neighboring observations to that specific observation. So wx and x, well, let's grab wx0 just to show. So these two things are not related at all, right? So the wx summarizes the surroundings of the first observation, and x summarizes the observation itself, right? If we look at the actual neighbors for kw0, we get that it has all of these 100 neighbors with this Gaussian kernel weight. Now, if we wanted it to be on the same scale as our input data, we have to do one additional thing. We have to row standardize it, and then construct the lag again. We'll do that here. I didn't do that in the notebook originally. So now, our focal observation for our first observation accommodates 2 people. But the 100 nearest Airbnb listings tend to accommodate around 3 people. Does that make sense? The focal observation, the first observation, has a review score rating of 100. But the 100 nearby Airbnb listings only have a review score rating of 92. Since we've constructed this kernel weights, all of these things become sort of de facto queries that we've done the computation ahead of time. Okay? So, using stats models, but you could use your favorite regression package and achieve the same thing. We're going to first check out our model, which is a standard OLS trying to predict prices using the attribute information that we had before. And we're going to get sort of not a very good model. It gives us an R-square about 0.29. We get most of our effects are significant except for the number of bathrooms effect. So I mean, obviously we're not using this to do any like inferential science on the theory of why Airbnb prices are what they are. But it would be interesting to note that bathrooms don't significantly affect Airbnb prices. But then, in addition to this, we'll construct a hybrid table together, this XWX table, which has, let's just grab the head. So this table has both our focal observations now, and then these lags, right? So for every single attribute that we're using, we're going to grab the lag attribute as well, and then we're going to use these together in a regression. And when we do that, we notice that the R-squared bumps a little bit. So we've done this feature engineering now. We've looked at constructing 100, the neighborhood average of 100 nearest observations, and we've gotten out this new regression where we find, indeed, some of these contexts are actually statistically significant, useful predictors, and we've improved our model in general. So for instance, when you're considering sort of the review scores, locally, the review score of the Airbnb matters, but the quality of surrounding Airbnb also matters. And in fact, that lag coefficient estimate is actually larger than the original one. So that sort of gives you an index of how desirable the area is, sort of in this intrinsic, unmeasurable quantity. We've sort of instrumented it with the neighborhood average of reviews. Does that make sense? If you're staying in an area with highly reviewed Airbnbs, it sort of gives us some information about that context in which that Airbnb lives. So there's an additional collection of functions in PySAL. These live under the PySAL spatial regression module. And these all involve various different types of spatially relevant specifications. So let's just fit one here on y and xwx table dot values. Oh. No, it's not going to work for, yeah. Okay, so there's some incongruousness between some of the stuff that we're working on in PySAL right now, but there are other methods such as these lag object, or sort of what they call lag regressions. So here, in the previous section, we just fit a linear regression that looks like this. And where this WX here reflects the neighborhood averaging that we've done, right? There's also another class of models that can be fit in PySAL and other places. You can fit them in Stan. PyMC is a little difficult. And this class of models fits instead a version kind of like our kernel regressor. And you can throw in a WX if you want, but you don't have to. Where you now have your outcome on both sides. And this sort of mixes the strength of the kernel regression, which borrows the similarity in the outcome to predict new outcomes. In this regression, you're using the outcome as an endogenous factor. You're saying that the price, nightly price of an Airbnb, cannot be determined by itself. You know, I am competing, if I'm an Airbnb tenant or Airbnb lord, whatever they call them. I don't like Airbnb lord, but I guess I'll use that. If I'm running an Airbnb shop and I'm pricing Airbnbs, I'm cognizant of the price of surrounding areas, right? So I don't have full price setting ability. In order for me to set my price, I need to be competing with the people that are spatially next to me, right? Because they have a similar set of amenities. They have access to similar urban areas, similar transit outcomes, right? So because of this, we can't necessarily say that we would expect all of these things to be independent of one another. And one way that we can model that is by this hybrid outcome method. Those get a little bit more complicated because they become nonlinear regressions. So mathematically speaking, there's probably not a way that we can efficiently solve this one in this particular kernel weights configuration. But there are ways as these get sparser to fit very well. So doing them on tens of thousands of observations, as long as you've got really sparse connectivity, works just fine. So this is what we have on the regression section. Are there any questions as far as what we've talked about on data borrowing as a conceptual method to bring in geography into your modeling using these kinds of neighborhood averages? No? Okay.
I have a question.
Yeah.
You mentioned Stan and PyMC. Is there anything like that in PySAL?
So I have written some stuff to sample spatial models in a Gibbs sampler for multi-level stuff. And I've also written some code to do some of this in Stan. We don't do, most of this stuff comes from maximum likelihood estimation perspectives. So in general, like we don't support Bayesian inference. Only the stuff that I've written as sort of packages under PySAL fit those kinds of models.
There's some Bayesian stuff in the smoothing we didn't get to.
Yes, true as well. There's looking at local smoothing of attribute weights, sort of more on either outlier detection or local area modeling that can get in that. But if you do want to, if you are interested in fitting these kinds of endogenous outcome models, I would suggest that usually there's some tools in Python. But I think it's probably best if you fit them in R. There's like a well-established Monte Carlo sampler there. Well, it's a Gibbs sampler, Metropolis within Gibbs. But the gradient stuff gets difficult because this reduces to a difficult expression to differentiate. So the conditional posteriors of the autoregressive component don't sample very well. So I just had a paper out last year, I think, that looked at that kind of stuff, and it's tough. Yeah?
The term you're using, data borrowing, refers to the feature engineering stuff?
Yes. So it refers to constructing new attributes either from WX or WY. Yeah.
And why is it called data borrowing? As opposed to weighted variables. Variables are sort of synthetic ways of
Yeah, I mean, you can call it what you like. I thought that data borrowing was a good descriptive name for what's going on. Formally speaking, yes, it is a form of weighting your exogenous covariates. But semantically speaking, your regression gains strength because you're borrowing additional information based on its spatial configuration of observations. So,
not increasing the degrees of freedom, presumably. That's the whole point.
yes, yeah, right. So you're not, I mean,
Not reducing.
yeah. So you're, well, I mean, you do get more parameters that have to be fit there. So technically you do lose degrees of freedom to fit those parameters. But in general, you're not making a more complex model. Yeah. So you can stuff it in any place where you use a linear model, which I presume is all places for most people. Any place you use a linear model, you can bring in geography by using these data borrowing techniques. This stuff, the endogenous regression is more difficult. In general, there's not a closed form solution depending on what you do. So like you have to use a different sampler if you want to do this in a logit situation. You can't fit it in particular ways in that way. Does that make sense? Any other questions? Y'all have a good idea about how you might apply this particular technique in your future linear models. Okay, so then we can move on to clustering and we can do the problem set. I'm going to ask another poll. Maybe not. We'll just do the clustering. So we'll move to 08. Is everyone following fine? Does anyone need a break? No? Okay. I guess you've been here for we've been here for 3 hours, so it's a long time. Is everyone on clustering? Yeah? Huh. That's strange. Yeah. So when it comes to clustering, Serge talked a lot about the stuff that we have in PySAL that will do map classification. And in traditional geographic perspectives, map classification is sort of a thing that we talk about for univariate data. When we're visualizing the structure, spatial structure of our distribution of data. And if any of you, this is only supposed to be an introductory workshop, so we're not getting too heavy into the theory of clustering in your data, but if any of you have used stuff like multidimensional k-means or other things like that, you know that it gives you this sort of dimension reduction technique. It allows you to take large amounts of data and express them in latent categories. It's kind of what map classification is supposed to do, but then we can do it with much more data than what we had before. So what I'm going to show you here is how to search for and use these clustering methods on larger data. Does that make sense? Cool. So the first thing we're going to look at, again, is this Berlin listings data set. And I'm just showing you again how this Berlin listings data set looks. And then we're going to pull up the scikit clustering module, which you should all have installed if you followed the directions. And again, I'm going to pull out a coordinate array. So most of the stuff that GeoPandas is useful for is to be able to sort of work with your spatial data. But again, scikit doesn't really care about where it comes from. It wants these NumPy arrays. So we kind of have to play nice with that. It would be nice if we could just send it a geoseries and it understood how to get the coordinate array. But it's definitely not there yet. So the first kind of clustering technique that you may have heard of is dbScan, right? This is a density-based scanning method that it looks at sort of local reachability, tries to find areas of high density and interconnection between observations and discover where sort of regions exist. So we're going to apply this dbScan just on the spatial information. So we're not going to consider anything about the attributes themselves. We're going to do what's called regionalization. Regionalization is slightly different from generic clustering. In a spatial context, regionalization is a graph partition. We're trying to split the data into contiguous, sort of geographically well-defined zones. And what dbScan applied to spatial coordinates will do is give us that. Right? Just like we usually use dbScan in feature space to give us well-defined zones with attribute similarity internally, this will give us well-defined zones where observations tend to be closer to one another in this zone than they tend to be outside. But that's only in the geographic dimension, not in the attribute dimension. So here we've applied dbScan to the spatial coordinates, and I've tuned the epsilon here. You have to do a hyperparameter search depending on the projection. It's not insensitive to that. So when you use these dbScan clusters, you get information about what the cluster discovers as the cores of every one of these clusters. So these would be, in other contexts like affinity propagative sampling, you'd get these things called exemplars. So when you hear core sample indices, these are things that are sort of like the most cognizant elements of that cluster. And then we get this label array. And as Serge was talking about in the map classifiers, this dot labels attribute is mainly what we're interested in, right? So we do these clustering applications, we get these labels, and then we use these labels in order to visualize complex patterns in the data. So here, what I'm recommending is that when you want to do this kind of study, you go through, you use your scikit classifier, you do whatever you want. Maybe you have a special model in Keras that you like. And then you can, again, pop it back down into GeoPandas and plot. So mainly what we're doing is we're going, most of the data analysis workflow is pull in your data, do some exploratory statistics to try and get your head around the spatial structure of the data, build some spatial weights matrices, and then use those to do all your data science. Bring it back into GeoPandas, plot, work with it, export it, make dashboards, things like that. So when we've done these clusterings in dbScan, what we've done here is we've shown that every single one of these are latent density clusters. So these represent areas where Airbnb listings are closer to one another than they are to any other one. And we see that mainly what we find is Berlin is a cluster, right? Well, tuning the epsilon value will give you different sort of resolutions on those clusters. It'll tell you how far apart observations need to be in order to be considered disconnected. So many of you may have heard of HDBScan, which is a hierarchical density-based clustering technique based on dbScan. Does some of this tuning for you, but also introduces more implicit parameters. The point of this was not to show you the best clustering. The point of this was to show you that some of these methods, when you apply them just on the lat longs, will give you these sort of zonations. And a lot of people want to solve zonation problems. So when you do these kinds of zonations, keep that in mind.
If you set the epsilon to a much smaller value, we get a lot more neighborhoods.
Yeah, or it would error because you don't get connected graphs. So like if we drop an order of magnitude from the clusterer and we pop it into the plot, we'll see that most of the clusters become either unaffiliated, which is now the purple, or so.
Yeah, so it's highly sensitive.
Yes, yeah, dbScan itself is highly sensitive to the structure of that. So one thing that I find to be helpful when I'm working with these kinds of classification labels is to sort on the labels, because when you get the classification vector back from scikit, you get -1 is like no classification found. So when you sort based on the labels, you can pop those below the rest of the map. It gives you a nice sort of impression of where those clusters are found. So here now, instead of saying at 1,000 feet, observations are going to be considered disconnected, now I've said at 100 feet, observations are going to be disconnected. And I've used that to sort of give us a sense of where these latent clusters of density exist. And if you look closely, you can actually tell that some of these neighborhoods correspond, or some of these clusters that are found by dbScan correspond to clusters of neighborhoods in the actual shapefile of the neighborhoods. But we're not necessarily going to get into that because, again, this is contingent on a lot of hyperparameters. Yeah?
I was getting the same visualizations as you, but I was looking at the cluster.p.
Yeah.
And it's coming up as none type. Shouldn't that be an integer?
It should be. Not sure. Originally, that should be a P. I'm not sure why that's the case right now. I'll have to check on that and get back to you. Sorry about that. Regardless, GeoPandas is smart enough that it knows how many clusters there are in a given discrete data set. So it'll figure it out. We don't have to tell it. Any other questions on just basic zonation of data sets? No? Okay, let's move on. So when you get actual aerial polygonal data, how many of you tend to work on like point data sets? Many, okay. How many tend to work on like aerial data sets where you've got districts? Okay, a couple. I think there's a lot of people who do like econometric stuff or program analysis that work on counties or zip file or zip codes or things like that. So a lot of this stuff is applicable to lattices, what we call them, these collections of polygons that touch one another. But in general, it's also applicable in theory to anything that's connected by an adjacency graph. So all of these lattice statistics are also themselves sort of graph methods, weighted graph methods, or what they call labeled graph methods, sometimes if a node has particular properties. Slightly different representations of the same thing that we're going to be talking about here. So again, we've got this neighborhood data set where we've got the median price of observations. And first what we're going to do is we're going to look for, just like we were before, do a map classification style approach. We're going to look for 3 clusters inside of the price data and the price data alone. If you recall, that's the median price distribution, right? So we should probably find maybe 2 clusters, maybe 3 clusters. Here I'm forcing it to be 3. You can do some assessment. We'll talk in a second about how that works. And now we're mapping what this distribution of median prices looks like when we're using this word agglomerative clustering on our input data. Again, still univariate, we're just visualizing the patterns in the price clustering. Have you all heard of the many different kinds of cluster certainty metrics like silhouette scores? Have you used them before? No, okay, so a silhouette score is kind of like a regularized distance, although it includes negative values as well. It's a measure of how certain we are about a given classification. It's a function of how close the observation is to the center of its cluster versus to the center of the closest cluster we could pick that is not that one. So it's kind of like we put it in cluster A, and our second best choice would be cluster B. How far apart is the observation from its own cluster to our second choice? Standardized, there's some stuff, it usually varies between -1 and 1. -1 indicates lack of fit, 1 indicates fit. And scikit has this silhouette samples function, which allows us to compute this measure of fit for every single observation in our sample. So here we get a measure of how strongly these prices that we fit before in this map are classified into their groups. So just like before, you can do sort of spatial statistics on these kinds of things. You can, map classify has some stuff relating to this as well, but we're not going to deal directly in terms of these silhouette scores for the moment. When you visualize based on the Fisher-Jenks algorithm, which is a k-means, so that's a different solver than the word agglomerative clustering, we get a different spatial distribution of our attributes, right? So depending on what cluster you think is relevant, here, this is using Ward. Here, this is using a Fisher-Jenks solver for class homogeneity. You'll see that you get different structures. In addition, our structure of certainty changes as well, right? So this silhouette map is quite different visually from this silhouette map. And again, we can do sort of map comparison techniques and statistical methods to compare these two things. And then, of course, you can plot these decision boundaries and see how these relationships vary across different clusterers. When you're trying to summarize the quality of an overall fit, you use a weighted average of the silhouette scores. So if you don't want to get the silhouette scores by observation and you'd rather just get a single map average estimate of how good your clustering is, you can use the scikit metrics.silhouette score function. And this will compute a weighted average based on the number of observations in each cluster of those silhouette scores propagating upwards. So as you see here, the Fisher-Jenks estimate, this k-means solution, is slightly better on homogeneity and separation than is the agglomerative clustering method. Okay, so these are just, again, we can do multi-dimensional versions of this because they're all just standard scikit clusterers, right? So if we wanted to then say fit, let's do an agglomerative because that's it's kind of simple. If we fit this agglomerative clustering and instead of using median price, oh wait, these are the districts. So we may not have as much information. Yeah, we don't have all of the information. So in this particular data set, I've only propagated up one attribute. I haven't propagated up more than one attribute. So here we're just dealing, but again, since these are scikit classifiers, you can take any number of features, condense them into a labeling set, and then use them to do this kind of certainty analysis. The second thing that's kind of helpful is, so we've seen zonation. We've seen when you use dbScan, you can just construct these sort of where are observations and how are they close to one another. Okay. We've seen that we can do this sort of map classification style approach where you look for high dimensional clusters in your data and you map the output of those clusterings. The other thing that you can do is actually look for zones that are homogeneous on a given attribute. And that's what I'm about to show you now. To do that, we usually need to, again, build a topological relationship. So I'm, again, going to use a particular adjacency graph. Here I'm using a rook adjacency. And rook adjacency is like queen adjacency, but it just means that you can only share an edge. So if two polygons share a point, they're not considered neighbors under rook, but they are considered neighbors under queen. Does that make sense? It's just an analogy to chess. We use it as sort of shorthand here. So I'm saying that I want to eventually find these clusters that are homogeneous based on their attributes, but then also I want them to be internally connected. I want them to form connected partitions of my global graph. And so to do this, we can fit our price clusters into scikit using this structure here. So in the agglomerative clustering function, you can actually pass a connectivity matrix. And PySAL constructs connectivity matrices from our weights objects on the fly. So when you look at, when you look at rook graph.sparse, this is a sparse matrix that represents the adjacency matrix in that weights object. So any of the various types of kernel weights constructions, KNN weights constructions that we have will also express themselves in terms of these adjacency graphs, which you can then use. You know, you can ship this off into Network X if you want to use sort of alternative types of graph partitioning. But this way you can go really quickly from fitting the adjacency structure in a spatial format like GeoPandas straight into scikit, right? So using these kinds of these methods. So what we're going to do is we're going to look for 3 clusters again, but we're going to make it so that it obeys this connectivity graph, this adjacency matrix. And we're again only going to find it in the median price. And we find 3 clusters with relatively homogeneous prices based on sort of the connectivity structure we fit. Now, you probably don't need to know a lot about Berlin to be able to tell me what this divide is. It's not actually precisely the correct divide, but there are some strong east-west divisions in Berlin.
If you know about Berlin, you also know why it's not exactly divided.
Right. Yeah, there's a lot that's gone on since then too. So in general, we can fit these kinds of clusterings, and again, you can vary the amount of clusterings that you find here. Say we wanted to find 6. You get 6 clusters that are adjacent to one another internally, but have relatively homogeneous prices. So in general, if you want to do this kind of weighted zonation, you can do it really quickly by moving straight from these connectivity objects into scikit. Now, one other thing that we can often use are these kinds of probabilistic clusterings, and scikit-learn has a really nice Gaussian mixture model framework. Anyone who uses Gaussian mixture models in other contexts, you can do the same exact kind of analyses. So here, I'm going to fit a Gaussian mixture classification just by, I'm forcing random state to be a particular value here so that we get reproducible results, passing along the price, and then we're going to give sort of a predicted price based on our mixture model. And the most helpful thing is that instead of using these silhouette scores, which are what they call a post hoc measure of fit, given the classification, we compute the silhouette score, we get these probabilistic measures of class membership. So here, this is actually built directly into the model of clustering. Most of the other clustering methods, like agglomerative clustering or k-means, don't actually think about the silhouette score while they're fitting. They only really think about these measures of variance, or these measures of deviation locally. Instead, this is actually built into the likelihood function of the Gaussian mixture model. So when we recover predict proba, which is how certain we are that, that this observation falls among one of these 3 or one of these 6 or one of these k classes, we get a full matrix of prediction strength. So here I'm going to use just a very basic argmax here. I'm going to grab the maximum class, and that gives us a sort of like a strength of label assignment here. And then again, we can make this visualization of how strong our map predictions are as well. Right? But one thing you'll notice is that in general, when we do these spatial clustering methods, we get these unconnected graphs, and we get these structures in the silhouette scores, which tend to not be very spatially patterned. Right? What happens if we compute the silhouette samples of things like the agglomerative method? Did I save it? Yeah. That's a bummer. I thought that this cell was there. I guess not. We'll go back to that. So the point is, anyway, when you visualize these things for the spatial versions of the zonation, when you get these homogeneous zonations, you'll find out that the spatial structure of the certainty is also very patterned. Right? So when you enforce spatial structure, you actually usually lose something in terms of the fit of the cluster. And here I'm showing you the relationship between prediction strength on the spatially constrained version and the Gaussian mixture version. But the point is, when you use the spatially constrained stuff, when you say, I want contiguous zones, those contiguous zones are usually never going to be as homogeneous as the zones that you don't force to be contiguous. So you have to be mindful. How much do you really want that contiguity? How much does that really matter to what the analysis you're doing is? Is it just for pretty maps? If that's the case, it may not actually be worth it, because the difference in the two can be rather stark. However, for the zonation stuff, you can move rather quickly from doing these topological computations in PySAL straight out to a matrix form into scikit using the tools that we've just talked about in clustering. Are there any questions on the clustering notebook? We've seen pure spatial clustering, attribute clustering and visualization, and then sort of what we would call regionalization or contiguous zonation, homogeneous zonation. No questions. This is a semester-long course rather than a 14-day course. But, all right. Well, we've got about 4 minutes, so I guess we'll break just a slight bit early. If you have any questions for me or my co-presenters, come up, talk to us. We'd love to chat. But otherwise, there's a couple more resources in the repository. Like I said, there's this additional case study. We've also got some additional teaching materials based on spatial data science and analytics in our various geographic data science repositories, and a book in the works. So yeah, please keep in touch and keep following us on more updates on this kind of stuff. Thanks.